Okay. So, good morning all. So, today I am going to cover the reconfigurable architectures. So, how these FPGA architectures will look like and what is the necessity of programming these FPGA architectures, how do we program these architectures, that I am going to discuss. Okay. Reconfigurable architectures. So, here the FPGA architectures are field programmable gate array architectures. Okay. It is a flexible architecture. So, we can change after implementation of the logic, we can modify the architecture, internal architecture can be modified. But whereas ASIC type of architectures, application specific integrated circuit, so that we cannot modify. Okay. So, once we program, once we design the chip, that cannot be changed at all, ASIC. Okay. So, but here different functionalities we can be implemented on the FPGAs easily. So, for example, this simple things like SPLD, simple programmable logic device, SPLD, you call it as SPLD, you know, already you might have studied in your BTech, PLD, okay, or SPLD, both are same. So, in this SPLD there are two types of architectures, programmable array logic, programmable logic array, PAL, PLA. Okay. So, both are actually two-level grid AND and OR gates, that is AND plane and as well as OR plane will contain these architectures. So, in some architectures AND plane is programmable, some architectures OR plane is programmable. In some cases both AND plane as well as OR plane is programmable. Okay. So, if you see this diagram here, the AND gate followed by OR gate. So, multiple, see AND gate here, multiple AND gates. Multiple AND gates and multiple OR gates. The AND gates are programmable. Okay. AND gates are programmable and OR gates are fixed here in this case. This architecture is actually I think PAL type of architecture, PAL. PAL architecture here only AND plane is programmable, OR plane is fixed. Programmable means here these fuses you might have seen the fuses, their fuse can be blown or fuse can be intact, that is the programming. If it is a blown means it is a disconnection of the input. If it is intact means that input is connected to that gate. So, for example, you want some input x bar. If you want to connect that input x or x bar to the gate, so whether suppose if you want to connect x to the AND gate input, then this fuse should be intact and the fuse should be it should be blown. That bloning is or intact or bloning is a programming. Okay. Right. Program connection between the gates initially used fuses or PROM also. Here the fuse technology, fusing and anti-fusing technology is very old technology. That is used in only the PLDs, EPROMs, fusing technologies. The latter technology is modified for the programming technologies. So, like a PROM programming, EPROM programming, flash programming, so then SRAM type of programming, these are the different types of technologies. So, now SRAM programming is the latest one. Okay, memory cell, that is read-write cell will be there, that in that cell if you write 1, so that will be connected, if you write a 0 it will be disconnected. Okay. So, but here these technologies like for example, if you see GAL, generic array logic, allowed to be reprogramming using EPROM and E2PROM, but that is erasable programmable read only memory type of. So, these technologies, it takes longer time for configuration of the chip or programming of the chip, it takes more time, that will increase latency, but whereas here the SRAM technology is faster. So, by using SRAM technology we can quickly program the chip, it is a configuration time. Next is CPLD, but here if you see PLD, what is the complexity of the logic you can implement in the PLDs? Only 100 gate logic. Normally complexity of the circuit will be indicated in terms of number of logic gates, 2 input number of NAND gates normally. So 100 2 input NAND gates logic complexity circuit. Complexity of a circuit is indicated through that 2 input NAND gate logic. So 100 gates logic complexity circuit can be implemented, 100 to 200 logic gate complexity. So if it is a beyond, suppose if it is a complex circuit 400 gates logic, that cannot fit into the chip. Okay. So that is why the next advanced technology here improvement is complex programmable logic devices. So in this complex programmable logic device, if you see the PLD types of blocks only, here this is one PLD, this is another PLD. So PLD types of architectures only. Sorry. So it is integrated. PLD types of logical blocks are integrated in a CPLD. Okay. So instead of single PLD, so now multiple PLDs like 4, 6 PLDs are integrated in and packed in a single IC. Now this IC will contain internally 4 PLDs. So that means single CPLD we can program up to, let us say 400 logic gate density circuit can be implemented in a single CPLD, or maybe 1000 logic gate density circuit also it can be implemented on single CPLD circuit, single CPLD IC. Complex programmable logic devices initially was a group of SPLDs and a single chip. More recent CPLD combine macro cells or logical blocks. Macro cells can implement array logic or other common combinational and sequential logic functions. So here logical blocks, each logical blocks acts like a macro cell. Macro cell is, each macro cell is and array of AND gates followed by array of OR gates only. So next is, but still the demand is even 1000 gate logic density chips also not sufficient of your development in technology, because still the demand for applications are more than 10,000 logic gate density circuits are required, or maybe 1 million gate logic density circuit. So we cannot place some hundreds of CPLDs on the board, it will occupy more space and cost also increases, the connection also will be difficult. So instead of that, so next technology is a field programmable gate arrays, okay, FPGA, field programmable gate arrays. So this is mid 1980s only. So but here, so we can implement circuit, millions of gate logic density circuits can be implemented on the FPGAs. This is the latest technology compared to your CPLD, PLDs, this is the latest technology. But here the basic leaf cell, that is the basic component, that is their macro cell, we call it as a macro cell. That macro cell is, see, any digital logic can implement in the form of a sum of product and product of some form, sum of products, SOP form and POS form, yes or no. So SOP or POS, here we require only AND gates and OR gates, okay. So that products we can generate through AND gates, AND plane. Then sum of these the products is OR gate. We require OR gate, AND gates and OR gates only. So that means basically in CPLD, SPLD, the basic cell of logic implementation is, so plane of AND gates, then OR gates, that's all. This is for combination circuit logic designing. But sequential logic circuit designing, you require one flip-flop. If you connect one flip-flop at the output, so then we can design any circuit, combination circuit as well as sequential circuit we can design. But here in this FPGA, so that technology little bit modified, instead of using that AND gates and OR gates, here basic element is different here, LUT type of basic element is there, LUT, lookup table type of logic is going to be implemented in this, okay. Yeah, if you see here, this FPGA, field programmable gate array, this misleading name, there is no array of gates. So the chip name is field programmable gate array of gates, okay, but actually if you see internally, there is no array of gates inside. Array of gates are there only in CPLD, SPL list only. Okay. So, in this FPGA basic element is lookup table type of logic only. This we call it as a CLB type of architecture, we are going to come that. Okay. Array of fine grained configurable components. Okay. So, that is CLB, configurable logical blocks. So, coarse grained and fine grained. Coarse grained RC architectures, array of coarse grained components. So, fine grained, coarse grained means the lowest level programmable component, fine grained. Okay. So, that is CLB. CLB is a fine grained component, configurable block. Coarse grained component is, so by using that fine grained component, they developed one coarse grained component, that is like a multiplier, is a coarse grained component. Okay. A DSP functional unit, that is a coarse grained component. These are the coarse grained components. That means programmable level at CLB or programmable level at little higher blocks, the coarse grained component levels. So, potentially larger capacity than FPGA, but applications may not map well wasted resources, inefficient execution. That is, see, for example, why do we require fine grained? Because fine grained means we can efficiently implement our logic, we can utilize complete resources, the properly we can use. But if it is a coarse grained operations, so some of the logic resources will be wasted for implement. Small circuit you want to implement, okay. So, but very big logical block is available, you want to implement a small logical circuit, so the remaining resources of that block will be wasted. Whereas if it is a fine grained, so we can interconnect by using multiple fine grains, we can design a complex logical circuit without wasting the resources. Okay. Yeah, if you see the very simple circuits here, how can we implement any circuit on FPGA? How do we implement this? Okay, for example, half adder is there or full adder circuits, you know already, a simple circuit. But how this can be actually, we are going to implement on the FPGA? How do we map the, see, half adder Verilog code you are writing, VHDL or Verilog code you are writing half adder, full adder or multiplier. But how this code is actually implementing on the FPGA circuit? How it is mapping? Okay, that I am going to explain. Okay, the first we will see combination circuit only. So, simple combination circuit, if you see half adder circuit, this is a truth table for half adder, 2 inputs and 1 output, okay, sum and carry outputs, you know that, okay. One XOR gate and one AND gate is required. So, here to implement this half adder circuit on a FPGA, we have to implement this on LUT. I told you know LUT is a lookup table. Lookup table is like you know multiplexers, 4:1 multiplexer, okay, 2:1 multiplexer. Okay, by using 4:1 multiplexer, so we can implement any 2 input 2 variable logic function. Yes or no? How do you do? So, for example, XOR gate I want to implement on 4:1 multiplexer. How do you do that? XOR gate I want to implement on 4:1 multiplexer. How can you do? I will give one 4:1 multiplexer, but you have to show the functionality of XOR gate. How do you do? Yeah. So, that selection inputs you have to connect to your variables. Variables are AB, XOR gate inputs are AB. XOR gate output is yes later, okay, yes or y whatever, okay. So, that inputs you have to connect to selection inputs of the multiplexer, S0, S1. The input of the multiplexers are I0, I1, I2, I3 is there, no. So, that means selection input S1, S0, 0, 0 is I0 will be selected, 0, 1 is I1 will be selected, 1, 0, I2, 1, 1 is I3 will be selected, okay. So, XOR truth table if you see 0, 0, what is the output of the XOR gate? 0, 0, 1, 1, 1, 0, 1, okay, 1, 1 is 0, that is the output of the XOR gate. That output of the XOR gate you have to connect to the input of the multiplexer, you have to hardwire, you have to connect output of the XOR gate, okay, 0, 1, 1, 0, that you have to permanently that I0, I1, I2, I3 of the multiplexer you have to connect. So, that means first input you have to connect to 0, second input you have to connect to second and third input you have to connect to VCC are 5 volts. Okay. So then last input you again you have to connect to 0. Then that S0, S1 inputs if you connect AB, then it will act like a XOR gate, the multiplexer. Yes or no? Understood this? Basic circuit only. So similar fashion LUT will work. LUT is going to work in the same fashion. Okay. So here if you see this half adder output sum is 0 1 1 0, carry is 0 0 0 1. So to map this onto the LUT, so LUT is again this is a 4:1 LUT. Okay. So in this LUT, 2 variables, the 4 storage elements will be there. So 2 input 1 output LUT. This is 2 input 1 output LUT. 2 input LUT means any 2 variable logic function you can implement on that LUT. Okay. So here if you see this LUT, so 4 cells are there, 4 memory storage cells. That each cell it can store only 1 bit. 1 bit can be stored. Okay. So just simply store this value, S value, S0110 is stored in this 4 storage cells. Storage cells is SRAM cell or memory cell. So just to store these 4 bits in the 4 cells, and these inputs are connected. So like AB connected to that memory address, because just think like this is a memory. Memory is 4:1 memory. 4:1 memory means what? What is 4:1 memory? 4:1 memory means what? Huh? How do you specify the memory? 4:1, 4 cross 1. 4 cross 1 means that memory internally it contains 4 memory cells. Each cell will store 1 bit. 4:1 means that. 1K by 8 memory means what? 1K by 8 memory means what? That memory capacity is 1K locations. Each location will store 8 bits. Okay. Similarly, so this is 4 by 1 memory. That means 4 locations. So each location will store 1 bit. Okay. And these 4 locations, how do we, to address these 4 locations, how many inputs are required? Address. 2 inputs are sufficient. So that's why that is the 2 input, 1 output LUT. 2 input. If it is a 2 input, so it can address 4 locations. If it is a 3 input, 8 locations, 4 input, 16 locations. So that means 2 input LUT we can design, we can implement any 2 variable logic. 3 input LUT, 3 variable logic we can implement. 4 input LUT, any 4 variable logic we can implement on single LUT. LUT, understood what is LUT now. So now for example here I want to implement sum as carry. These 2 you have to implement. So for that I require, so 2 input 1 output LUTs, 2 are required. So one is for sum, other is for carry. Okay, this is sum implementation. See for example 0 1 1 1 0, and these are the AB input, this is the output. Similarly carry also same. Okay. Any questions here? Understood this? Huh? Okay. Right. So now suppose if it is here in this case is that LUT output is only 1 bit output, 2 input 1 output. If it is a 2 input 2 output LUT is available, then if you see this is a 2 input 2 output LUT. 2 input 2 output LUT, suppose if it is available, so then we can implement both sum and carry in a single LUT. Okay. Half adder sum and carry we can map to single LUT, but that LUT should be 2 input 2 output. Okay. So AB 2 inputs and 2 outputs, the sum and carry of half adder, that means your half adder implementation now it requires only 1 LUT. Similarly if you go for full adder ABC, 3 inputs and 2 outputs, sum and carry. So that LUT requirement is here 3 input 2 output, 3 input 2 output LUT we can implement this okay, both sum and carry. Both sum and carry of one bit adder, it can be implemented on single LUT, 3 input and 3 input in 2 output LUT. Just lookup table mapping only. This is LUT. So that means here in the LUT what we are writing, output function of the truth table, sum and carry. Output of the truth table we are writing into that internal storage of that LUT. This is internal storage. This is internal storage of the LUT memory. So this each memory can store 2 bits, 2 bits. That is, one is sum, other one is carry. Sum, carry, sum, carry. Output of this 1 bit adder, sum and carry we are storing. Then that inputs we are connecting as address inputs to this, like address memory, and the output is so like a sum and cout. Okay, right. So that means so programming means what here? We are 1 bit adder. If you want to implement on the FPGA means what you have to do? Simply 1 bit adder output, whatever the input, suppose if you give that inputs ABC inputs, all possible combinations inputs, that corresponding output of sum and output carry, that you have to store in that LUT cell, that's all. Then that LUT will act like a 1 bit adder, that FPGA will act like a 1 bit adder. So programming is what? You are programming these bits. 1 bit adder if you want to implement on FPGA means you just simply load these bits into that LUT. That is the programming of the chip or implementation of the 1 bit adder in the FPGA. Is it clear? 1 bit adder implementation on the FPGA is simple. Simply you store these bits, the bit stream, the sum bit stream and carry bit stream, you have to store in a that LUT of the FPGA. That is nothing but so implementation of your 1 bit adder on the FPGA. Okay, programming of the FPGA, configuration of the FPGA or mapping of 1 bit adder circuit on the FPGA is that only. Okay, but only thing is how to generate this output bit stream and how do we store into that FPGA, that only you have to see. So for that you are going to use the tools, okay, VBODO tool or maybe Xilinx tool or Altera tool. You are writing the code, Verilog code, VHDL code, and simulating. After simulation you are generating the bit stream finally. The bit stream is these bits only. These are the bits are there, no? These are the bits. These bits are, after generating these bits, we are programming the FPGA, that's all. Programming means the bits will go and sit into that LUT. Understood this? Why are not FPGAs just big? For example, see 3 input, 2 output LUT we have seen. But if it is a 6 input, 7 input, 8 input, 10 input, see variables. See? 3 input means 3 variable A, B, C or X, Y, Z. 4 input means X, Y, Z, P. 4 variables, 5 variables, 6 variables. But 10 variables, is it possible? 10 variables, 20 variables. If it is a 20 variable, so 20 input LUT is required. But now, as of now, the latest FPGA if you take, so the number of inputs are only 6 input LUT only available. Even latest Zinc FPGA or any ultra scale Kintex FPGA if you take, so right. So number of inputs are only 6, limited to 6. But why not more? Why not more? Just now I told. Why not more means suppose 8 input. Why can't we 8 input LUT? Huh? No. 8 input LUT means 8 variable logic can implement in single LUT. But why are not that LUT is not available in FPGAs? Why that FPGA manufacturers are not implementing, not designing 8 input LUTs? What could be the reason? Why are not FPGAs just big LUT? Just now I discussed this point, the previous slides. Coarse grained, fine grained, just now I discussed. What is coarse grained? coarse grained CLB, fine grained CLB. If all CLBs are only coarse grained, what is the problem? Huh? See, for example, in your chip on IC, all gates are 4 input gates only available, okay? But you want to design some 2 input logic function. How do you do? All gates are there in the IC, this is one IC, this IC internally all 4 input gates only there. But I want to design one 2 input logic function. How do you do? Huh? So actually 4 input is a very little bit complex logic, 2 input is simple logic, but some of the 2 inputs maybe we can ground or maybe connected to VCC or maybe unused and we can implement, but that is unnecessarily wasting of the resources. We are wasting small functions we cannot implement on big circuit, we can implement small functions, but it will waste the resources, unnecessarily wasting of the resources, okay. So that is why if 8 input LUTs or 6 input LUTs, so for example 4 variable logic you want to implement. 4 variable means you have to use 6 variables, 6 input LUT you have to use, the remaining 2 inputs the logic will be wasted, okay. So that resources are wasted here. So if it is a optimized, for example complex, depending upon the complex, earlier complexity logic designing is only 4 variable, okay, 4 input LUT is sufficient, okay. So but now it is increased up to 6 variables, 6 variable, but if you want 12 variable logic you want to implement, okay, we can combine these 2-3 LUTs and we can design 12 variables, 8 variables also we can design, combining the LUTs we can design up multiple variables, right. So that is optimum size, okay. If it is all are 8 variables, so unnecessarily that logic resources will be wasted if you are going for lower variables, okay. Lower means, for example all 6 are available, your logic is always never go for 6, most of the logic is you are implementing only 4 variables. So that means almost, so 2 input variable logic will be wasted, okay. Yeah, size of the truth table grows exponentially based on number of inputs, 3 inputs 8 rows, 4 inputs 16 rows, 5 inputs 32 rows, okay. LUTs grows exponentially based on number of inputs, but number of SRAM bits also, because I told LUT means SRAM bit only, memory cell is a bit, SRAM bit. So 2 power I, LUT we can represent like this, 2 power I into 0, where I is number of inputs, O is number of outputs, 2 power I, okay. Example 64 input combination logic, 64 input combination logic with 1 output would require how many SRAM bits, okay, 2 power 64, 2 power 64 memory bits are required, SRAM bits, okay. That is 1.84 in 10 power 19 bits are required. So this type of LUTs are not feasible, that is not a solution to design that exponentially growing of that LUT size, okay. So but suppose if 5 input LUT or 4 input LUT is there, that can be cascaded by connecting this, we can design a multiple input logic can be implemented, okay. So if you see we can map circuit into multiple LUTs, okay, divide circuit into smaller circuits that fit into one LUT, input and outputs. For example, if you see this circuit 3 input 2 output LUTs, so but here see how many blocks, 1 2 3 4 blocks are there. So this single LUT is not sufficient, we cannot fit this complete circuit in a single LUT, we require multiple LUTs. If multiple LUTs we can map this circuit, okay, easily. So if you see because suppose if you have in your FPGA 3 input and 2 output LUT is available, so simply we can map this block in a one LUT. This block can be mapped to one LUT because here, so 3 inputs, what are the, this is one input, these are the 2 inputs, so total 3 inputs and 2 outputs. one LUT. Okay. So similarly, this is another, okay, and 4 LUTs are required to implement these top blocks. The next block is here, here one LUT and this another LUT. So, but here again still, if you see, we are still that 4 LUTs we are using here, the 3 input to outputs it is mapped exactly, but here if you see here this one, 2 input 1 output only, 2 input 1 output only, okay, but this one is 3 inputs 1 output, this is fine. So this is 3 inputs, here 2 inputs, here 1 input, okay, understood, right? So right, 3 inputs 1 output, this here again 2 inputs 1 output only. So that means here how many LEDs are using total number of LEDs in this circuit, how many LEDs? Huh? How many LEDs are? 6 LEDs, but still 1 LED is not utilized 100%, okay. So 3 inputs, 2 outputs you are not using, only 2 inputs, 1 output is using, remaining all are, we are using 3 inputs, 1 output. 6 LEDs are required to implement this circuit. What if circuit does not map perfectly, more inputs in LUT than in circuit, so then what you have to do? More inputs in LUT than in circuit. That means LUT contains 3 inputs, suppose your circuit contains 2 inputs. How do you do? So with the help of truth table, the functionality other input we have to, whether you have to ground or whether you have to 0, that you have to do with the help of truth table. Okay, we can do that. Other input if you have to ground or other input you have to make it logic 1 without changing the functionality. So we have to map the circuit into that. More outputs in LUT than in circuit. So extra output simply not used, that's all simple. Okay, the space is wasted, so should use the multiple outputs whenever possible. Yeah. So one important point here, you just tell me the number of gates in a circuit has no effect on the mapping into a LUT. So all that matter is the number of inputs and outputs. So unfortunately, it is not common to see large circuit with a few inputs. See, for example, if you see this one gate, 3 inputs, 1 output, that is common. But here 1 lakh gates or 10 lakh gates, 10 lakh gates, that circuit, is it possible with 3 inputs and 1 output? Huh? Some 10 lakh gates or 1 million gates, logic circuitry, just only 3 inputs and only 1 output. Is it possible that type of logic circuitry? What possibility is there in this? Multiple gates, thousands, 1 lakh gates. So, but the inputs are only 3, output is only 1. Okay, it is not common. You see, it is not common to see large circuit with a few inputs. It is not common. Normally, it won't. Okay. Normally, 3 inputs means 3 variables. Okay, maybe logic circuitry, maybe 8 gates or 10 gates logic circuit only we can design, but not some 20 gates, 30 gates, 40 gates, 50 gate circuitry with just 2 inputs or 1 input out, 1 output. Okay, and that means, so whatever I discussed just now, so if it 3 input 1 output is 1 LUT I told, but even this circuit also is going to fit into that LUT, single LUT. No, LUT, yeah. So if you no, answer is both of these circuits can be implemented on single 3 input 1 output LUT. Is it possible or not? Single LUT only it will take 1 million gates. 1 million gate logic can be implemented on a single LUT. Huh? What is? Huh? Huh? How it is possible? It's not possible. Okay, all redundancy. So, okay, so it is not possible. See, LUT itself is only few gates logic density, that it is that input output only relation. If you maintain only input output relation, okay, so number of inputs and number of output, based on that one LUT if you decide, okay. So, but logically if you say that, okay, number of inputs are 3, 1 output, okay, 3 input 1 output LUT is sufficient irrespective of internal number of gates, okay, but it is not feasible at all, okay. So, logically if you see, okay, it may be, seems to be, if you just by seeing this, okay, it may be possible, but if you are trying to map onto the LUT, it won't work. But that will not arise at all, it will not exist at all. This type of circuit may not arise at all, okay. But logically it seems to be okay, because we are just maintaining only input output relations, only 3 inputs 1 output, but irrespective of how many gates are there, we are not caring at all, okay. How to handle sequential? So, this is up to, okay, clear for you everyone, okay, that is for combinational circuit. But sequential logic circuits, how do we do? Sequential logic circuit is any sequential logic circuit, okay, counters, resistors, state machines, so all the sequential circuits designing. So, that only LUT is not sufficient, that is only for combinational, but sequential logic. So, here one flip-flop is connected the output of that LUT, one flip-flop, with that flip-flop it is possible any sequence circuit we can design by adding one flip-flop at the output of the LUT. So, it can support both sequential and combinational circuit, okay. Add a flip-flop to the output of LUT. So, here if you see 8-bit resistor using 3 input 2 output LUT, okay, 3 input 2 output LUTs by using a simple resistor, 8-bit resistor, x of 0, x of 1, that 8 bits. Register means, what is register, what is the meaning of register? Register, counters, you know, shift register, okay. So, what is register means? Group of flip-flops, okay. So, that flip-flops connected in the form of array, it will store the bits. Register means it can store, we can store the bits in registers, or we can shift the bits, we can store and we can shift. Register means that it will hold the data, okay. So, for example, if you want to design 8-bit register, means 8 flip-flops are sufficient, 8 flip-flops are okay. If 8 flip-flops are there, means we can design 8-bit register, okay. So, but in that case, how to implement 8-bit register? By using the 3 input 2 output LUTs. But what is the purpose of lookup table here? Because here flip-flop is connected, not independent, it is connected at the output of the LUT. Flip-flop is, if you see here, the flip-flops are connected at the output of the LUTs. But if you want to implement an 8-bit register on a FPGA, how do you do then? How many LUTs it will take? How many LUTs it will take? How many LUTs are required to implement 8-bit register on a FPGA? See the circuit diagram, 3 input 2 output LUT. Each LUT is 3 input 2 output. How many LUTs are required? 3 input 2 output LUTs, that is one cell size. How many that LUTs are required to implement 8-bit register on a FPGA? By see the circuit diagram, you can tell, no? How many are there? It is written there, 3 input 2 output LUTs. How many are there in this? 4, then why are confusing? See, 4 are there, no, directly. 4 LUTs are required. 4 LUTs are required to implement that 8-bit register on FPGA, okay. So, here see the connections, but x of 0, x of 1, x of 2, x of 3 uniformly it is connected, but each LUT one input is not used, 3 input, okay. So, here if you see 2 outputs, because here Why can't we use that third one? Why can't we use third input? We are not using that LUT third input. Where it will be stored third input data? There is no flip-flop, only two flip-flops only are there. So only two inputs only are used, because the output is only two flip-flops, right? If the three flip-flops are there, then we can use third input also. Okay? Output is only two flip-flops, right? So that's why only two inputs, just that LUT is just only passing that input data to that flip-flops only, simple. Okay? Simply it is passing this x of 0, x of 1 is loaded into this flip-flop, x of 0 is loaded in this flip-flop, x of 1 is loaded in this flip-flop, right? So then in that case, if you connect x2 here, that x2, if you connect here x2, where it will be stored? There is no other flip-flop in this, only two flip-flops are, okay? Understood or not? Okay, fine. So that's why that third input is not used. But here lookup table function is simple only, yeah, you can see the next slide. So lookup table function is simply passing the data to flip-flop, that's all. We are not using any functionality in this. It is the unnecessary waste of lookup table only here. So this LUT, x of 0 is connected to this flip-flop and x of 1 is connected to this flip-flop, okay? LUT is simply passes input to the appropriate output, x of 1 and x of 0, y of 0, y of 1. And third input is, so third input, because here 3 inputs are there, because 3 input LUT means 3 input LUT means how many cells will be there inside? How many storage cells? Three input LUT, internally how many memory storage cells? 2 power 3, 8, okay, 8 storage cells. So that's why this selection input, one of the input is, this is not used actually. This one is not used, we are not using at all, okay. Third one is not using. So just only this 0, 0, 0, 1, 1, 0, 1, 1 we are loading, and that value is go to y1, y0. Okay, if you write 0, 0, 0, 0 will be stored. If you write 0, 1, 0, 1 will be stored. If you write 1, 0, okay. Sequential logic. So it is not waste to use LUT for a registers here. Yes, because we are wasting this LUT. This is only simple connection only. Yes or no? We are wasting that LUT resources, right? So this LUT functionality is simple, only just passing the data. So wasting of the resource, yes or no? Yes. Okay. So waste to use LUT for a registers. But how do we do? Yeah, we'll see. Commonly used for pipeline circuit, that this type of circuit, see, because here if this LUT is basically, if you see, LUT followed by flip-flop. But can we design? So that means all outputs, whatever you implement in this circuit is always, the output is flip-flop output only you are going to get, or full adder circuit or off adder circuit or any combination circuit if you design, the output is flip-flop output only it is going to get. But that is not required for all circuits. That means that is, we call it as a registered output, we call it as a registered output. We do not require all applications registered output. Registered means stored output, registered, but because output is a sequential, registered output. But we require pure combinational output. For all applications we do not require registered output. But if your LUT is, like this, all outputs are registered outputs, because output is through flip-flop. It will store. Registered output means, so the output will be stored. but all applications we do not require registered output. But how do we do then? We require only pure combinational output, not through flip-flop. See, for example, full adder. Full adder output is combinational, sum and carry. We require only combinational output, not through flip-flop. Okay? That means you have to bypass the flip-flop. Okay? Some circuits sequential, if you are designing a sequential, so then you have to use registered output, sequential circuits. Combination circuit, combinational output only you have to use. So that means one bypassing is required, you will see. So here if you see, this is registered output, the adder and output register are combined, not a separate LUT for each. So for example here, this is pipeline adder. Pipeline adder circuit, so plus pipeline adder means you require adder followed by a register. Pipeline adder, one addition or any operation, multiplication, addition, division followed by a register. Then again one addition, subtraction, multiplication followed by a register. So that is a pipeline operation. So there this is useful, okay. But other normal operations, so that combination followed by flip-flop is not required, okay. So existing FPGA do not have flip-flop connected to LUT outputs. Why not? Flip-flop has to be used. Impossible to have a pure combination logic. That's what I mean. Okay. So if flip-flop C is present, then it will add some delay also, and because all combination circuits we require a clock also. Our combination circuits require a clock. Okay. So to avoid that, no, because if flip-flop is present, then we have to use clock, okay, right. To avoid that, the actual solution is this one, CLB, okay. That is whatever I discussed just now, LUT followed by flip-flop, that is for understanding purpose. Actual circuit is not like that in FPGAs, just for understanding basics. That I explained, that LUT followed by flip-flop, but actual circuit inside the FPGA is different. So that circuit is this one, configurable logical block, CLB. Okay. So CLB configurable means we can program that, we can modify configuration. The CLB is the basic FPGA's functional unit. The basic functional unit is CLB. Like universal gate, you know universal gates. What are the universal gates? NAND and NOR. Why are calling universal gates? Why we are calling those universal gates? Okay. Any logic function, fundamental gates, AND or NOT function. AND or NOT can be implemented functionality. AND or NOT functionality can be implemented using these gates. That means any gate, any logic function can be implemented. Any functionality can be implemented by using that universal gate. Similarly, these logic blocks, universal configurable logical blocks. These blocks also we can use to like universal gates type. We can design any logic function by using these blocks. By interconnecting these blocks, so any logical function, combinational sequential logic function we can implement on the FPGA. Okay, universal logical blocks otherwise. These universal logical blocks are configurable logical blocks. Okay. If you see here, what is the difference between that previous circuit and this circuit? The CLB and previous whatever we discussed. So if you see flip-flop is also LUT followed by flip-flop, and flip-flop output is connected to one multiplexer, 2:1 multiplexer is it, okay. So by using 2:1 multiplexer, we can connect combinational output, this is the output finally, either we can connect combinational output or flip-flop output. Through flip-flop, that means we can bypass the flip-flop. If you want combinational, so you can select this multiplexer to this input. If you want a registered output, you can select this flip-flop output. Okay. So by selecting the multiplexer selection input, so we can select either pure combinational output or we can select the registered output, flip-flop output also. So that is the modification is made in the CLB. Okay. If you see here, okay, CLB internally it contains not only this circuit, not only one LUT, it contains multiple LUTs. Multiple LUTs is present inside the CLB. See, the multiple LUTs. So two LUTs, 3 input, 2 output, 2 LUTs. How they are connected here? The cascading. So this output is connected to again this input of this. One more multiplexer at the input side. So like that, the latest CLB internal it contains some 16 LUTs, 32 LUTs are present in single CLB. Okay. So that means even one LUT itself we can implement any 3 variable logic function. But if you connect like this, how many variables here you can implement here? So here 3 are there, here also. So maybe sharing with this, okay. How many variable logic function can be possible here? Okay. So by cascading this, we can implement multiple variables, okay, 5 variables, 6 variable logic function easily we can implement by just connecting single CLB. Okay, that each CLB or each LUT. So even though if it is only 3 input, 2 output, only 3 variable, but by with the help of cascading, we can go beyond. Okay, so 5 variables, 6 variable logic function also we can implement easily. Okay. Efficient way of handling common IO between adjacent LUTs saves routing resources. So because this is internal connection only, this connection is internal, otherwise we have to connect externally. So but this in the CLB it is internally it is connected. Yeah, if you see ripple carry adder, if you want to design a ripple carry adder, 1 bit adder, each LUT implements one bit adder, one full adder, 1 bit. One full adder can be implemented on each LUT. Each LUT we can implement one bit adder. Suppose if 8-bit adder you want to design, how many CLBs are required? Okay, right? In the CLB, because here just we assume that CLB contains 2 LUTs. 1-bit adder we can implement easily in single LUT. So in each CLB how many bit adder we can implement? 2-bit adder. Okay, 2 full adders otherwise. Okay, 2 full adders we can implement on single CLB. Okay, so that is C, AF0, BF0, CF0, AF1, BF1. Okay, this is sum 0, sum 1 carrier. 2-bit adder. 2-bit adder we can comfortably implement on single CLB. If that CLB contains two LUTs, just 2 LUTs. But actually if you see latest, so more number of LUTs are present. Yeah. If you see Xilinx Vertex 4 CLB, Vertex 4 is what is Xilinx? Xilinx actually manufactures these FPGAs. Xilinx is one company, organization name that will manufacture the FPGAs. Okay, that FPGA name is Vertex 4. Okay, in that Vertex 4 FPGA CLB, okay, consists of 4 slices. Okay, one slice equal to 2 LUTs plus 2 flip-flops. IP. Okay, Vertex 4 CLB consists of 4 slices. Each slice is 2 LUTs. Okay, so but then each CLB how many LUTs then? You just see that, read carefully that. Read carefully. vertex not 4 CLB, don't read like a 4 CLB. That vertex 4 is different. Vertex 4 is FPGA name. Okay, vertex 4 CLB. Don't read like a 4 CLBs. Okay, vertex 4 is FPGA name. That vertex 4 FPGA CLB internally contained 4 slices. Each slice is 2 LUTs. How many LUTs total in each CLB? What is this here? What I am thinking of that? 8 LUTs, it is written also there. Vertex 4 CLB is 8 LUTs. One CLB of that vertex 4 FPGA is internally 8 LUTs are there. Each LUT we can implement 1 bit adder. That 8-bit adder, ripple carry adder we can implement in one CLB only, single CLB. Single CLB sufficient to implement configurable logical block. It is implement one 8-bit adder easily, comfortably. So that means this type of CLBs, thousands, millions of CLBs is inside the FPGA. That is the gate density I am saying. See, complexity of the logic can implement on the FPGA is, okay, millions of gates. Okay, you just see here one CLB 8-bit adder. Each adder how many gates? Let's just assume 1-bit adder, how many gates are there? Total number of gates in 1-bit adder. 1-bit adder, how many gates? Sum and carry both. 1-bit adder, how many gates? Three input XR. Okay, all 2 inputs you can take, let us say. 2 input gates. XR, sum is required to XR gates. Carry, how many gates are required? So 2 input gates, AND gates 3, and then 2 input OR gates 2. So 3 plus 2, 5 plus 2, 7. 2 input gates I am just telling, 2 input gates, 7 gates. 1-bit adder designing, 7 gates are required, but all 7 gates are different. Actually this will not work out like normally. So the gates complexity will be counted all equal, similar type of gates only, equivalent 2 input NAND gates. 2 input NAND gates only will be counted normally. Okay, but here we are OR gates, AND gates are there. Okay, no problem. So equivalent NAND gates. Okay, NAND gates. So that means 7 gates. 7 into 8-bit, 56 gates. Because 8-bit adder, no, this we can implement 8-bit adder. 56 gates density is possible in single CLB. 56 gates density logic can be implemented in single CLB. This type of CLBs, thousands, millions of thousands of CLBs are present inside the FPGA. The millions of gate density logic can be easily we can implement on the FPGA. Okay. So, but this is for Xilinx. Similarly, Altera is also one more organization. Altera also manufactures FPGAs, but Altera that FPGA name is different. Okay. So there this internal architecture also little bit different than Xilinx FPGA architectures. So in Altera we call it as a lab. Lab is logical array blocks. In Xilinx FPGA we call it as a CLBs. In Altera we call it as a labs, logical array blocks. That is the only difference, but otherwise everything is same inside. Any FPGA if you take, this only the logic, basic logic is same. Okay. Okay, I will stop here, then we will go for a break, then later I will continue. If we just connect all fixed wires with CLBs, we cannot program whatever we want to connect that CLBs is not possible. Some flexibility is required in the connections also. So for that programmable connections we can establish between the CLBs. So main challenge is should be flexible enough to support almost any circuit. If FPGA does not know which CLB will be connected, where does it put wires? Okay, which CLB will be interconnection, where that wire should go, that will be known, put wires everywhere referred to as a channel wires and routing channels and routing tracks, many others. Okay. So, here there are these channel names, we call it as a routing channels, routing wires or channel wires, routing channels and routing tracks. CLB is typically arranged in a grid with wires on all sides. Because all CLBs will be in structural manner, all will be arranged in the form of a matrix, and these wires also will be placed, so in all sides of the CLBs. These wires are horizontal and vertical, okay, and like a interconnection, like a tracks, road, paths, houses will be, all houses will be connected with one straight road. Then again one horizontal road, colonies we might have seen. Same similar fashion here. So, each CLBs are connected with this type of all straight horizontal wires and vertical wires. We have to place these wires, but we have to connect that. We have to connect that CLB to these wires. That wires are placed horizontally, vertically, all, okay. But with programming option, we have to connect the CLB to these tracks. So, that means, so here this is the wires, okay, horizontal and vertical roads, like horizontal vertical roads. So, here this output of the CLB we have to connect the input of these tracks, fixed wires, but flexible connections, that is possible through how to connect CLBs to wires. Solution is connection box. One connection box is required, that connection box is present inside the PGs. This is the connection box, the device that allows inputs and outputs of CLBs to connect to the different wires. This is one connection box. With the help of this connection box, there is internally this CLB output will be connected to this CLB, or this CLB will be connected to some other CLB. The connection box are going to be used to interconnect the CLBs. Interconnection means one CLB output is going to input of another CLBs. Okay. So, we will see that this interconnection, how it is going to be done. Okay. This is a connection box characteristics, the flexibility. The number of wires a CLB input and output can be connected to, flexibility 2, flexibility 3 is there, if you see the connection box. So, that means this CLB can be connected to any one of these two vertical lines. This junction is, this is one junction, this is another junction. So, that means this CLB output or input, this are the CLB wire. The CLB wire will be connected to any one of these two lines. Either it can be connected to this wire or this can be connected to this wire. Similarly, this wire will be connected to any one of these two wires. So, here the two junctions. Okay, here this also see CLB any one of these two wires. So, that means your flexibility is 2. That means we can connect any one of the two wires. The choice is 2. We can select one. Flexibility is 2 here. Okay. Similarly, here flexibility is 3. That means this wire can be connected to any one of the 3 wires. 3 wires, either you can connect here or you can connect here or you can connect here. Okay. Similarly, here this CLB. So, here flexibility is 3, flexibility is 2. Which is better? Flexibility 2 or flexibility 3? Which is more, 3? More options are better or 2 or limited options are better? Then you have to say that, okay. Flexibility 3 is better, more flexible. See, more, so we can, whether we can connect this wire to any one of these 3 wires, more flexible. Okay. Yeah, here topology, if you see connection box characteristics defines the specific wires each CLB IO can be connected to, same flexibility or different topology. Topology is changing now. So, compared to previous circuit, this is a previous circuit, this wire is connected to any one of these adjacent 2 wires. This wire also will be connected adjacent 2 wires only. Here also if you see adjacent 3 wires. Okay, we can connect any one of these 3 wires. But here in this case topology change here, topology. Okay, if you see define the specific wires, each CLB IO can be connected. Example, same flexibility, different topology. If you see this is adjacent, same, this is flexibility 2, flexibility 2, here also flexibility 2 only, here also flexibility 2, but topology changed. So here this wire can be connected to the first wire and third wire, first or operation, not and also possible. We can connect single wire to 2 wires also, or we will connect it to any one of the wire also. Okay. So here it can be connected to the first or 3, here also this first or 3, this topology changed. So the different types of the switch boxes or connection boxes are possible, different characteristics of these connection boxes. Okay. The connection boxes allow CLBs to connect to routing wires. Okay, routing channels or routing wires I discussed now, this one, these are the routing wires, routing channels or routing wires. Okay. So CLBs with the help of connection box we can connect to routing wires, but that only allows us to move signals along a single wire, not very useful. That just by connecting this with the help of connection box, connecting to routing wires, that will not solve our problems completely. Okay. How do FPGAs connect wires together? So connection box allows CLBs to connect to routing wires, but that only allows us to move signals along the single wire, okay, but not very much useful. How do FPGAs connect wires together? So that is, for that one more box called switch box. This is also present inside the FPGAs, switch boxes. The switch matrices connect horizontal and vertical routing channels. So, but here we are just connecting with the help of connection boxes, we are connecting this CLB wire will be connected to these channels, vertical channels only one wire we are connecting. This wire is connected to this, either this wire or this wire, that is all. Okay. But that is not sufficient either for connections. So then switch boxes, switch matrices connect horizontal and vertical routing channels. Horizontal and vertical will be interconnected through the switch boxes. You should know the difference between connection box and switch box. Connection boxes are connecting to only either horizontal or vertical connection, that is all. CLB will be connected either to vertical wires or it will be connected to horizontal wires by using connection boxes. But switch boxes are connecting these horizontal vertical wires, interconnection between horizontal and vertical switch boxes. Okay. Here switch boxes, switch matrices connect horizontal and vertical routing channels. Okay. So how it look like? See, if you see, there are 2 types here. One is planar, other one is Wilton type. There are 2 configurations are there. Okay, topologies defines which wire can be connected. Planar subset switch box only connects same channels. The planar connection is, see, these are the horizontal wires, horizontal 0, 1, 2, 3, vertical 0, 1, 2, 3. So here 4 wires horizontal, 4 wires vertical are there. So we can connect these 4 horizontal wires, 4 vertical wires, right? So with the help of these switch boxes, so that in these 2 configurations are 2 topologies. One is planar topology, other one is Wilton topology. In planar topology is 1-to-1 connection. 1-to-1 connection means 0 wire will be connected to 0 wire. 1 wire of this horizontal will be connected to 1 wire of vertical. 2 wire will be connected, second will be connected to second of this. 1-to-1 connections only it is possible. Okay. Horizontal, this 0th line will be connected to 0th line of vertical. 0, 0, 1 to 1, 2 to 2, 3 to 3 only connections are possible. This is planar type of switch box. But whereas Wilton type, if you see, this is a different. Wilton switch box connects different channels. 0 will be connected to 1, or 0 will be connected to 2, 0 will be connected to 3. Okay. Similarly, this 0 will be connected to 0, 0 will be connected to 1, 0 will be connected to 2, and 0 will be connected to 3. All possible combinations are possible here. So, this 0 line we can connect to either 0 or 1 or 2 or 3. Similarly, this 1 will be connected any one of these 4, or this 1 will be connected any one of these 4. All possible combinations are possible. Out of these 2 switch boxes, which is preferable, which is better, planar type or Wilton type? Wilton is more flexible, more possible combinations are possible compared to planar. If more flexible, more possible connections, this is better way of routing. See, that means your FPGA number of routes we can comfortably route easily. It will be routable. All connections can be easily connected. If you use this type of switch boxes, sometimes it may not connect all channels. Some channels will left over. FPGA will not. The tool will not able to route all the channels. Okay. This type of switch box is better at present. Yeah, if you see some example also there. So, why do flexibility and topology matter? Routability means all connections you have to make. Routability means every connection will be, whatever the connection, possible connections, everything should be possible within that FPGA. FPGA means very small device. So, only what you call 10 mm, 1 centimeters, maybe 20 mm by 20 mm, let us say, okay, or 30 mm, 3 centimeters, okay, maximum 3 centimeter by 3 centimeter or 2 centimeter by 2 centimeter, some 1 million connections it has to route. How it is possible? Okay. So, right, within that it has to do, so all connections it has to route, the tool has to route, that connections are possible without shorting or by maintaining minimum distance between the tracks, it has to be able to connect all the CLBs. That is the routability or routing. Okay. So, here if you see, why do flexibility and topology matter? Routability measure of the number of circuits that can be routed. Higher flexibility, better routability. Flexibility is more means we can route easily, all connections can be made. If flexibility is limited, flexibility means routing is difficult. Okay. So, Wilton switchbox topology is better routability. Okay. So, if you see here, this is one line, I want to connect to this line. This line of CLB, this wire of this CLB will be connected to this wire, destination is here. So, here if you see one-to-one connections, because flexibility 2 switch topology, adjacent topology, by that means here this line can be connected to this wire or this wire, any one of the wire can be connected. So, because here if you see this is connected like this, second wire is possible, this connection is possible. This routability is okay, fine here. It can be possible by using flexibility to this type of switch box. But whereas if you see here in this case, yeah, that is the same thing it is shown here, the routability, higher flexibility is better routability, Wilton switch box topology is better routability. So, this is the connection I have seen, but next is if you see this one more, so this source line I want to connect this line, is it possible now? This line I want to connect. By using this line I want to connect to this, by using this type of switch box, is it possible? Because this line will be connected only these two, either this or this, both those two are not connected here, these two are connected to these two. So, right, it is not routable, it is not possible to connect this, it will fail. So, this is a planar switch is failing here, okay, not possible to route from source to destination, planar switch is failing, not possible to connect this, you will get error. Okay. But whereas if you go for other type of switch here, it is we can route that. Wilton type of switch if you use, this can be connected, or otherwise more flexible switch, 3 flexibility switch if you use, then it is possible. Okay. Yeah. Switch boxes, short channels, long channels. What is short channels and long channels? Short channels means useful for connecting adjacent CLBs. Now this is adjacent CLBs, these connections short channels. Okay. So connecting between CLBs, that wires we call it as a long short channels. So but here these long channels is useful for connecting CLBs that are separated, these long CLBs, okay, that is the far away CLBs connecting through long channels, okay. Useful for connecting CLBs that are separated, allows for reduced routing delay for non-adjacent CLBs. With the help of these short channels, long channels, allows for reduced routing delay for non-adjacent CLBs with the help of these long channels. Short channels used for connecting adjacent CLBs. Right. Now if you see, not only CLBs are there in the FPGA, in addition to CLBs, what else is there? This is CLB, configurable logical blocks. That means logic can be implemented in these boxes, CLBs. Green color boxes are used for implementing of your logic. But in addition to that, there are routing channels, horizontal, vertical, like roads, I told you, know, routing wires, horizontal, vertical routing channels. But that interconnection of those is possible through, what is this box, blue color box? Connection box. Connection box are used for connecting of the CLBs to these wires, horizontal wires and vertical wires. Then one more is there, switch box. Switch box are used for interconnection between vertical, interconnection between horizontal lines and vertical lines. Okay, interconnection between horizontal and vertical lines, that these switch boxes and connection boxes are present in addition to CLBs inside the PG. Only this much or any other is required, you will see. So here two-dimensional array of CLBs and programmable interconnect, sometimes referred to as a island style architecture. Island style architecture. Okay. So can implement any circuit, we can implement any circuit of this type of thing, but should fabric include something else? FPGA fabric, but this is sufficient or any other circuit also still required. Memory. Next is memory. So could use flip-flops in CLB to create memory, because every CLB output is one flip-flop is there. That flip-flop is a memory only, it can store one bit. One flip-flop will store one bit, that is a memory. If 5 flip-flops are there, 5 bits we can store. If 10 flip-flops are there, 10 bits we can store. So can we use that flip-flop as a memory? Suppose I want memory of some 10 bits I want to store inside the FPGA. Can I use those 10 flip-flops to store the 10 bits inside the FPGA? Okay, we can use, we can store. Okay, that we will see. So for example, here create 1 megabyte of memory. 1 megabyte means 1 megabyte of memory I want to create inside the FPGA. So each LUT contains one flip-flop. Okay, how many LUTs are required to create 1 megabyte of memory inside the FPGA? How many LUTs it will occupy? Okay, so for example, 3 input, 2 output LUT. Each LUT is 3 input, 2 output. That means it can, each LUT can store 2 bits only. How many LUTs are required to create 1 megabyte of memory? So here 1 mega means 10 power 6 into 8 is 1 megabyte. Byte means B per byte. Byte means 8 bits. That means each location is 8 bits. 1 mega is 10 power 6. 10 power 6 locations, each location of 8 bits. So but then how many LUTs are required to create 1 megabyte of memory? So that we can simply divide, because here if each LUT it can store only 2 bits. If you convert that 1 megabyte into number of bits, 1 mega is 10 power 6 into 8, that bits. 10 power 6 into 8 is the bits. That bits divided by 2 bits. Okay. right? Understood or not? 10 power 6 into 8, that means or 8 into 10 power 6, otherwise you can write, okay. 10 power 6 into 8 by 2, that means 4 into 10 power 6 again. 10 power 6 is 1 million. 4 billion LUTs are required to create 1 megabyte of memory inside the FPGA. But each FPGA internally, I told how many LUTs are possible? Not millions of LUTs is not there, only thousands of LUTs may be possible, 10,000, 20,000 maybe LUTs only, not million LUTs, okay. So, not possible. See, 1 megabyte of memory we cannot create inside the FPGA by converting LUTs into memory. So, this is a very bad idea. We cannot do like that. We cannot convert LUTs, or LUTs will not convert LUT into a memory, but only small memory is okay. Okay. Suppose if you want to store 1K bits or maybe 100 bits or 1000 bits, so that may be okay. Some 50 LUTs you can convert and into memory, that is fine. But LUTs is actually required for functional implementation, not for storage purpose. Functional logic implementation purpose only we can use LUT, so, right. So, but what is the solution now? So, FPGAs commonly have a tens of thousands of LUTs, large devices have a 200K LUTs, that is all. So, even if FPGA were large enough, using a chip to implement 1 megabyte of memory is not smart, okay. This is a bad idea of converting LUTs into memory cells for storage purpose. So, then what else? Solution is use LUTs for logic, not for memory, okay. So, LUTs are just an SRAM. Xilinx refer to a distributed RAM, we will see, okay. Solution 2 include distributed RAM we can create. Distributed RAM we can create by converting LUTs into memory, but that is a limited memory, okay, few bits. Solution 2 include dedicated RAM. So, dedicated RAM components in the FPGA fabric. So, Xilinx refers to as a block RAM. So, that means one dedicated memory blocks are inserted inside the FPGA. That memory we call it as a block RAM to solve that memory problems, okay. Some dedicated memory blocks are present inside the FPGA to store your data. That memory we call it as a block RAMs, okay. So, here Xilinx referred as a block RAM, can be a single or dual port, okay, and can be combined into arbitrary sizes, can be used as a FIFO. These block RAMs are actually, it is configurable, again it is, this is a flexible block RAMs, okay. We can combine each block RAM, there is some fixed size, the 4K bits, okay, block RAM. So, that can be, we can combine 2 block RAMs and we can create 8K, combining, we can increase the size by combining the blocks, okay, or otherwise we can increase, we can create multiple ports, but it can be a single or dual ports. Single port means, dual port means what? What is single port and dual port? RAM. Single port RAM, dual port RAM means what? Huh? What is single port RAM? Dual port RAM. Port means what? Data. We can read and write from the memory. Okay? If it is a single port, so that means we can read or write at a time. Only we can read or only we can write. If it is a dual port, we can read, write at a time we can do. Both can be done simultaneously. Read and write is possible at the same time. But if it is a single port, either we can read or we can write. Only one operation can be done at a time. If it is a dual port RAM, so we can do both at a time. Read and write operations it can support at the same time. We can create 2 ports. Okay. Then we can also convert that RAM into distributed RAM into FIFO, because some FIFOs are required in the FPGA sometimes. First in, first out type of memory block. Okay, block. So for that we can also use these block RAMs as a FIFOs also. We can convert that. Okay. Altera, this Xilinx is block RAMs. Altera we call it as a Altera Cyclone 2 as a MK4 blocks. That is the same block RAMs only in Altera FPGAs. So that size of the memory is normally 4K bits. 4K bits. I am saying not a bytes. Each location it stores only 1 bit. 4K bits. Okay. So if you see the diagram, okay, architecture. So this BR is a BR, that BR is a block RAMs. These BRs are all block RAMs, block of memory. So now one more extra cell is added to the FPGA fabric. So we have studied this ELB, this connection matrix, switch matrix and block RAM. Okay. Block RAM can be placed anywhere, typically placed in columns of the fabric. So column wise, typically placed in the columns, block RAM. These block RAMs are for to store the data, memory. We can use these as memories. So, but we should not convert this CLB to a memory. Okay, we should not convert this CLB or LUT not be converted into memory, because these memories are dedicated memory blocks are available inside the FPGA. That is block RAM, and by converting this CLB into memory, that memory we call it as a distributed RAM. Distributed RAM is CLB also, each CLB, how many LUTs are there in each CLB? Just now I shown in Vertex for FPGA. How many LUTs? 8 LUTs. Each LUT how many bits it will store? 2 bits. Okay, if it is a 2. Okay, 3 input, 2 output, 2 bits. 2 bits means, so how many bits we can store in each CLB? How many bits we can store in each CLB? 16 bits. 8 into 2. 16 bits. Each CLB you can convert into 16 bits RAM. Okay. Not only that, even for the input are 4 variable logic, 3 input, 3 variable, let us say. 3 variable LUT means the input, how many inputs? 3 variable, 3 input LUT, how many input cells? How many input memory cells will be there? 3 cross 2 LUT. So LUT is 3 input, okay, 3 input LUT, 3 input and 2 output, 2 output LUT. Okay, that is 3 inputs means what is the size of the LUT here? This is 3 inputs. This is 2 outputs, 3 inputs, okay, 3 inputs, 2 outputs. What? How many cells inside? Huh? How many cells will be there in this? So 8, okay, 8. It's like 8. 0, 1, 2, up to 7, 8. Each cell will store how many bits? 2 bits. 2 bits we can store. So, but each LUT, how many bits we can store? Each LUT we can store, this is 3 input 2 output LUT, each LUT how many bits we can store? Huh? How many bits we can store? See, each LUT we can store 2 bits, 16 bits, okay, not 8 bits. Each LUT we can store 16 bits. 16 bits store, we can store 16 bits, okay. But each CLB, how many LUTs are there? 8 LUTs. In each CLB, how many LUTs? 8 LUTs. 8 LUTs means how many? Each CLB, how much memory we can create? 8 into 16. 8 into 16. Okay, how much? Huh? 8 into 1 16, 128 bits. Okay, each CLB we can create 128 bits of memory. That memory we call it as a distributed RAM. Distributed RAM. You can also create not only flip-flop, output flip-flop, this cell, LUT cell also we can create as a memory. Okay, output flip-flop we can store anyhow 1 bit, that is 1 bit only, but this LUT itself we can convert into memory. So that memory is 128 bits for each CLB. But that is for whatever I told, but 3 input LUT, 3 input, 2 output LUT. But the latest Zinc FPGA or ultra scale FPGA 6 input is there. 6 input LUT is latest FPGA, 6 series, 7 series FPGA. LUT size is 6 inputs, not 3 input. Okay. So 6 input and 1 output. 6 input, 1 output. Okay. 1 output or 2 outputs. We have to see. I think only one output only. Please. Okay. Next is FPGA is commonly used for DSP applications also. We can use for DSP applications also. Normally, not only logical implementation, simple logic design, digital designing, but DSP logic also we can implement on the FPGAs. For DSP implementations, what we require for DSP applications? So multiplication and accumulation, multiplier operation. So multiplier and accumulation is the most of the time we will use in DSP applications. Okay. So that block also present inside the FPGA. That is, we call it as a DSP 48 in Xilinx. Makes sense to include custom DSP units instead of mapping onto LUTs. So that means instead of using LUTs for implementing your DSP function, DSP FFT, convolution, filter, instead of converting your LUT for DSP operations, we can use DSP blocks also present inside the FPGA. That DSP block is DSP 48. Okay, what is that it will do? It includes multipliers, adders, subtractors. Okay, 18 cross 18 multiplication, 48 bit addition subtraction. These two operations are provided inside the DSP block. This block we will call it as a coarse grained, that is a fine grained, this is a coarse grained block. Fine grained block is CLB, and these block RAMs and these DSP blocks, these are coarse grained blocks. Okay. This provides efficient way of implementing addition, subtraction, multiplication, multiply and accumulation operation, barrel shifter, FIR filter, routing operation, square root operation. So all these functions we can efficiently we can implement on the FPGA by using this DSP block. So okay, so these DSP blocks also present inside the FPGA. If you see that the pink color blocks, DSP blocks. Okay. So this total we call it as a FPGA fabric. Programming of FPGA, we'll see how to program the FPGA. How to program configure the FPGA to implement circuit. So far we have mapped the circuit onto the FPGA fabric. Now is the technology mapping. The process of converting circuit in one representation into a representation that corresponds to a physical components. FPGA components, what are the FPGA components now? LUTs, gates, gate level, see circuit diagram, full ladder circuit if you draw, XOR gates, okay, AND gates, OR gates. So how to, but in FPGA there is no XOR gate, AND gate. Inside the FPGA we don't have these things. Inside the FPGA what is there? LUTs, RAMs, DSPs, these blocks are there. We have to, that we have to map this. We have to map this, whatever logic circuitry, you have to map to that components. Okay? So mapping is all gates will be mapped to LUTs. Okay? Memory, block, memory, array declarations, the storage, in arrays you will write in the program. Okay? Data storage. So that will be mapped to block RAMs. Okay? Then multiplications will be mapped to DSP. If any multiplication operation is there, that will be mapped to DSP function. But we need to some way of configuring each of component behave as desired. How to store the two tables in LUTs and how to connect wires in a switch boxes, we will see. Include flip-flops in a fabric to control programmable components. Need a way to select the mux. So here I told you this CLB, basic CLB, either we can get the output combinational, pure combinational or registered output, but that is through by selecting this multiplexer. That means multiplexer selection is a programmable. Multiplexer selection is programmable. That means either we can select pure combinational output or we can select registered output. Yeah, that is a flip-flop. There is a one, that is the one switch is there, one switch is required. That by using that switch we can select either combinational or we can select registered output. But this switch is here technology. Technology I told initially. What are the technologies? Fusing, anti-fusing, ROM, PROM, EEPROM, or flash memory or SRAM memory. But SRAM memory is the latest technology now. Okay? So this flip-flop here, whatever it is shown, that is one SRAM cell. SRAM cell. If you write 0, it will select multiplexer 0 input. If you write 1, multiplexer 1 will be selected. Okay? We want to select either multiplexer 0 input or multiplexer 1 input. That is a combinational circuit input or flip-flop output. That is a registered output. So that is a programming. Programming is, what is programming here? Programming of that cell. That binary bits you are going to generate, that binary bits, so it going to sit into that cell. Okay? Yeah. Now this also interconnection I just discussed, this fabric. But the junctions are there, no? These junctions. The junctions are interconnections. These junctions are interconnections. That should be programmable. Actually, it will be programmable. Interconnection is programmable. If you write 1, it will be connected. If you write a 0, it is not connected. Okay? So all the cells will be present there. Memory cells. All SRAM cells are going to present at the interconnections. Okay? So if writing 1 to that cell, the connection will be made. If writing 0, disconnection, open. Then FPGA is programmed with a bit file, binary file. Finally, after writing Verilog code, then after simulation, synthesis, everything you have done, finally you are going to generate bit stream, bit file. That bit file only it is going to be programmed with the FPGA. That bit file only it is going to sit all these memory cells. Okay? The bit file whatever you are generated and programming, that bit file it will go sequentially and it is going to store in all these memory cells according to your logic circuitry. So here file containing FPGA program with bit file containing all information needed to program the FPGA, contains bits for each control flip-flop, that is the control flip-flop. Also contains a bit file for fill LUTs. I told you, LUT inputs you have to store according to your functionality. First initially I discussed full adder sum, full adder carry. So that bits are there, no? So those bits also will be stored. that bits will be, it will be stored in that input flip-flops, input storage cells of the memory. Okay, we will see. So, but how do you get the bit file into the FPGA? So, more than 10 LUTs, LUTs are 10,000 or maybe 20,000, 100,000 LUTs are there. How that bit file will go into that FPGA and it will store? Okay. So, if you see, so because these are all CLB, in each CLB LUTs are there, but these bits, how these bits will go and store, how many pins are required to store these, how to store these bits into each of these CLBs. Okay. So, because here all CLBs are spread across the chip, but how do we store the bits into this? How do we store these bits? How do we store these bits into this box? How do we store these bits into this box? That bit file. Okay. So, that will be stored in the form of a scan path. Okay, this path. Configuration bits input of here, it will go like this. In a scan path, it will go and it will store. In a sequential manner, the bit stream will go inside the FPGA in the scan path, then it will be stored inside the FPGA. It will not go completely in parallel fashion, bit stream. Okay. So, because that the huge number of CLBs, the bit stream also very lengthy, they make a huge shift register out of all programmable components, LUTs, control flip-flops, and shift in bit file 1 bit at a time. That is why this configuration, it takes some time. That delay we call it as a configuration latency delay, initial delay. To configure the chip, that program the chip, it takes some time. Why it is taking time is because that bit stream, it has to go in this fashion across the FPGAs. Okay, example also, if you see simple example. So, this is full adder, the simple full adder, it is not working, over. Okay, this is full adder, if you see, this is a full adder. So, the full adder lookup table input, what we have to store? The sum or carry, the sum bits, all the sum bits you have to store in this, all carry bits you have to store in this. Okay, and also one control flip-flop is there. So, this is for selection of combinational, because this is a combinational circuit. So, how many bits you have to program this now? 8 bits per sum and 1 bit per control flip-flop. Similarly, 8 bits per carry and 1 bit per control, 9 bits, total 9 bits you have to generate. Total 9 bits for full adder implementation, complete full adder implementation including sum and carry, how many bits? 18 bits. Okay. So, it will go like this, that 18 bits stream, 1 bit at a time it will go, bit by bit it will go like this. Okay. That is all, that is a program. LUT is programmed now, it will function like a full adder. But this is a very simple circuit shown, but entire FPGA also programmed in this fashion only. Okay. Right. Reconfiguring a FPGA is slow. Shifting 1 bit at a time not efficient. Reconfiguration. So, bit files can be greater than 1 megabyte. Eliminates one of the main advantages of reconfiguration. RC is reconfigurable. So, partial reconfiguration with shift registers, entire FPGA has to be reconfigured. Solution, I think problem first you should understand. You understood the problem? Huh? Reconfiguring the FPGA is slow, but reconfiguration means if you load some bit file, then later you want to modify and again you have to load new bit file, it takes time. Okay, and runtime we cannot do at all, real time, runtime, we have to off and again load, runtime we cannot change, but the FPGAs are actually runtime reconfigurable. Okay, that means partially reconfigurable, dynamic reconfiguration, this is the features are available. but this will not solve that, it will not use that features here. If you do like this bit by bit, if you reconfigure, this eliminates one of the main advantages of RC, partial reconfiguration. With the shift registers, entire FPGA has to be reconfigured. That takes time. What is the solution is, in vertex 2 allows columns to be reconfigured, and vertex 4 allows custom regions to be reconfigured. Requires a lot of user effort, better tools needed. So partial reconfiguration we can do. Partial reconfiguration. We need not reconfigure the entire chip again. So already we reconfigured, you just modified only 1 or 2 bits. If 1 or 2 bits means that 1 or 2 bits only you have to reconfigure. Why do you need to reconfigure the entire chip again? Okay? So that partial reconfiguration is possible only in 1 or 2, the latest FPGAs, not all FPGAs. So vertex 2 and vertex 4, that is where this vertex 4 also not latest, was. So vertex 7 is there, 8 is there now. LUTs with many inputs can implement large circuits efficiently. Why not just use LUTs with many inputs? Just that we discussed initially. High flexibility in routing resources improves routability. This is a trade-off. See, why not use LUTs with many inputs means? So, because small circuits, the LUT inputs will be underutilized, not utilized. So if it is a small LUTs are there, we can interconnect and we can implement large circuits. Okay. So what is the optimal number of inputs are required? That only that is present inside the pitch. Optimal. Most of the large circuit that is implemented with, let us say, 4 input. So 90% of the circuit you are implementing with 4 input means 4 input LUTs is present. Some FPGAs internally it contains 3 input LUTs, 4 input LUTs, even 5 input LUTs, like the different input sizes also present. But some FPGAs only fixed size. For a Zinc FPGA, it 6 input LUTs, all are 6 input LUTs. Okay. High flexibility in routing resource improves routability, that we know. Flexibility, we see in switch matrix, connection matrices. Okay. So more flexible means routability is more. So we can route 100% easily. Why not just allow all possible connections? Answer: architectural trade-offs. Anytime one component is increased or improved, there is a less area of other components. Yeah, the trade-off you have to maintain. So that means if larger LUTs, less total LUTs, less routing resources. More number of, see how many LUTs, 100K, 200K or 500K or 1000K LUTs. What is the size? Size is, if more number of LUTs if you place inside the FPGA, but placing of other logical blocks like a memory blocks, DSP blocks, routing channels, the space will be reduced. This is a trade-off you have to maintain, that's all. Okay. Similarly, more block RAMs, less LUTs and DSPs. More DSPs and less area for LUTs and less block RAM. That is the optimal number. Some area for block RAMs, some area for DSP, and most of the area for LUTs. So like that, and also some area for routing of the wires. Like that, it is planned inside the FPGA. Okay. Yeah. If you see this one question, simple question. Determine best LUT for following circuit. That best LUT size. Either we can go for 4 input 2 output LUT or 5 input 2 output LUT. Which one is best? Either we can choose first one or second one. So first one is constraint also there. The constraint is a delay 2 nanoseconds, and the third one is a delay is 3 nanoseconds. 5 inputs are there, but delay is more. But first one is 4 inputs are there, delay is less. But which one you will choose? And one more constraint is, first one is it will take number of transistors, that is area. Number of transistors are area. The area of the first LUT is 192 transistors, and 5 input LUT 384. How do you get that 192? We are getting that 192, 4 input LUT. Why it is multiplied 6 multiplied by 2 per 4 multiplied by 2? Number of transistors. Assume each SRAM cell is 6 transistors. 4 input means how many cells? 2 power 4, 16 cells will be there. Each cell it stores each cell it stores 2 bits. That means 2 RAM cells are required. 2 RAM cells. Each RAM cell how many transistors? 6 transistors. Okay, 6 multiplied by 2 power 4 multiplied by 2. That is 192 transistors per each LUT. 4 input LUT. 5 input LUT, 384 transistors area. Okay, area, this is area, that is the time. Then area and time optimization. Time optimization delay 2 nanoseconds and 3 nanoseconds. Area is 192 and 384. Now tell me which one is better for mapping of this circuit, combination circuit, either 4 input LUT or 5 input LUT in terms of delay or in terms of area. You see the solution? This is the solution. 5 input LUT, suppose if you use 5 input LUT if you use, so we require 2 LUTs, because here 4 are there, here 3 are there, 3 inputs and 4 inputs, 2 LUTs are required. 2 LUTs means total area 768 transistors are required. Total area is 768 transistors. Okay, delay is concerned 6 nanoseconds. Why 6 nanoseconds? Not 2 by using 2, but it is one output of one is connected to input of other one. So if you see this takes 3, this takes 3, first one, this one is takes, I think it is not visible. This mouse is not coming. Yeah, this one takes how much time? This LUT 3 nanoseconds. This LUT will take 3 nanoseconds, but should not say that 3 plus 3. This because here this is taking 3, and this output of this is connected to this gate. Okay, so that's why this 3 plus 3 are. Otherwise, if it is both are in parallel, only 3. It is a cascaded connection. So 6 nanoseconds. Okay. Next one, if it is a 4 input LUT, the 4 input LUT, because here 384 only, 192 plus into 2 transistors, and the propagation delay is 4 nanoseconds. Now 5 input 6 nanoseconds, 768 transistors, area is more, delay is more, 5 input LUT. If you go for 4 input LUT, area is less, delay is less. So then which one is better? 4 input LUT is better. Okay. Now this one, determine best LUT for the following circuit. Which one is better? Tell me for this. You decide and tell me. So first apply 4 input, then see what is the transistors and delay. Then next you apply 5 input and test number of transistors and LUT and tell me which one is better. First is 4 input. If you take 4 input, how many LUTs are required for 4 input? 2. 2 means 2 into 192. 2 into 192 transistors, 384. 384 transistors are required. Delay 2 plus 2, 4 nanoseconds. 4 nanoseconds delay. If it is a 5 input LUT, how many LUTs are required? 1 or 2? 5 input LUT, if you use one LUT is sufficient, 2 input or 2 LUTs I have to use. If it is a 5 input LUT, 5 input LUT is only 5 inputs only there, no? How many inputs are there in this circuit? In the circuit, how many inputs are there? 5 inputs, one single LED is sufficient, 5 input LED is sufficient. If we use 5 input LED, number of transistors are 384, okay. Delay 3 nanoseconds. So transistors are concerned same. Transistors are, whether you go for 4 input or 5 input, same number only, 384 only, okay. But delay wise, there if it is a 4 input, it is 4 nanoseconds. If it is a 5 input, it is 3 nanoseconds. So it is faster. So then you have to go for 5 input LED. Here 5 input LED you have to go. Okay? Yeah. This is another circuit is there, okay. Large LED is fast when using all inputs, waste transistor otherwise. Okay? Fast when using all inputs. That is the 5 inputs, all 5 inputs we are using, it is fast. Okay, otherwise it will waste. You must also consider total chip area. Wasting transistors may be okay if there are plenty of LEDs. Vertex 5 or vertex 6, vertex 7 also uses 6 input LEDs. Kintex also, it is using Kintex, Artex, all this zinc FPGA, it is using 6 input only, 6 input LEDs. Vertex 4 uses 4 input LEDs. Okay, right. How to design FPGA fabric? There is no overall best. Design fabric based on different domains. DSP, then DSP one type of application, DSP application, and high performance computing one type of computation, high performance computing and embedded system. These are the 3 categories of applications. One is DSP type of applications, and second category is high performance computing applications, parallel processing, high speed operations, high performance computing. And third is embedded type, embedded computing, embedded system type. So for Xilinx there are 3 different types of devices. One is LX, other one is SX, and third one is FX. Yeah, hello sir, Bhaskar ji. You are starting now. I'm going to complete maybe at 1 o'clock train only. So yeah, I'm still in the class. Okay, I'm going to finish within 4-5 minutes. If possible, I will reach other. Otherwise, okay, sir. Thank you. Okay, Bhaskar. Yeah, wait for few minutes. I am coming. Okay, LX for logic, SX for signal processing, and FX for embedded systems. When you are selecting the FPGA, you have to see this LX series or SX series or FX series. Depending upon the application, you have to choose that the corresponding FPGAs. That's all. Okay, right. I will close this session now. So then maybe meet again in the afternoon. Afternoon, I am going to again this FPGA related stuff only, but one processor design I am going to explain. Complete processor design. Okay. So So, brief introduction I will give, okay, what is CPU, what is GPU, okay. So, I forgot in my pen drive, okay. So, you know what is CPU, what is GPU, okay. CPU is central processing unit, GPU graphical processing unit, okay. The architecture of the central processing unit and the graphics processing unit, comparing their structures, cores, memory architectures and processing capabilities, we will see, okay, little bit. So, CPU is constructed from billions of transistors, okay. The CPU can have multiple processing cores, okay, and is commonly referred as a brain of the computer, okay. It is essentially to all modern computing systems, as it executes the commands and the process needed for your computer and operating system. You know, CPU is main component of a computing system, okay. It contains multi-core CPUs, single core CPUs, the different architectures, okay, VLAW architecture, pipeline architectures, parallel processing architectures, different types of processor cores will be present. So, GPU is, what is the difference, main difference between CPU and GPU, okay. CPU is actually internally it contains the highly sophisticated computing architecture is present in the CPUs. Cores are maybe multiple cores, but cores are limited, maybe octa core, 8 cores or 16 cores maximum, okay, 16 cores, 8 cores, but each core is highly, each core capability is almost high processing computing capabilities there in each core. There may be a floating pointer or maybe complex operations. It can be done very fast, okay, in single cycle it can be able to compute complex operations, highly sophisticated architecture with the pipeline and everything will be there. But whereas in GPU contains multiple processing units, multi-cores, thousands of cores is going to present. CPU is only maximum 16 cores or 8 cores processing, but each core is high computing power, high processing power for each core. But whereas GPU cores thousands of cores, but each core is limited processing power. Each core processing power is limited, that is, so a simple processing element is present in each core. So, maybe the GPUs we can use for graphical processing, see image processing application, video processing or machine learning these days, okay, pixel processing. So, there each core is a simple processing, but thousands of processing elements is present in the GPU, okay. So, these thousands of processing cores is going to work in parallel. That means simple processing only, maybe multiplication and addition operation only. Addition, subtraction, multiplication, this is only simple operations, integer operations or maybe floating point operations. But whereas processor cores are not like that. Internal architecture highly pipeline, highly processing, super scalar, super pipeline, okay. So, that type of architecture is in the CPU cores, okay. So, GPU is or graphic processing unit is a specialized electronic circuit designed to rapidly process and manipulate memory to accelerate the creation of a digital image, because GPUs have thousands of smaller cores, okay. So, compared to CPUs, GPU architecture is optimized for parallel processing, okay. So, GPU can handle multiple tasks simultaneously and are faster at graphical and mathematical workloads, okay. Thousands of operations can be done in parallel in GPU architectures, okay. Yeah, see, they have an example just for easy understanding. CPU is like latency, optimized latency. CPU is like one high speed car, okay. CPU processing is high speed car, okay. So, optimizes latency, we can, CPU is very less number, but it can do very fast computing, faster car, speed, high speed. But GPU if you take throughput, see GPU throughput, I do not know whether it is multiple, okay, maybe processing, but that latency, yeah, optimize latency. So, that means that can be through GPU, we can travel through CPU. See, it is a very fast, but limited persons only can be traveled, very high speed latencies. Okay, multiple people can be placed one place to other place. Okay, multiple persons. Okay, maybe it can be moved from one place to other place. So that maybe we can go through a single car with high speed car. Okay, or we can go through a multiple bicycles. Okay, 100 persons you want to transfer from, for example, NIT to Kashipet. You can give 100 cycles. Okay, so the 100 people will go through that 100 cycles. Or other way, with one car, you can very quickly you can transfer. Each time at a time 5 you can 20 trips. 20 trips the car moves from here and there. So all 100 people will go. So that is the analogy here. Simple analogy. CPU is like a high speed car. Okay, GPU is also a small processing engine, but multiple processing engines parallel. Yeah, okay, if you see the difference here, the CPU is control unit, it is going to present control circuitry and common controller logic and cache memory, and as well as the processing cores, high speed processing cores like ALU, that 4 ALU, green color ALU, 4 cores. But these 4 cores are very powerful cores, high speed processing engines. But whereas GPU, if you see that green color, so many processing engines are there, CPU cores. Okay, the small processing elements only, that will not that much capable of that CPU, not on par with the CPU cores. This is only simple processing engines, multiplication or addition type of simple operations can only, it can be done with this, but thousands of cores are present in this. Okay. Low compute density CPU, high compute density. Okay, compute density means multiple operations can be done faster. Okay, multiple operations can be done in parallel, high compute density. Okay, thousands of multiplications can be done in parallel in case of GPU. But here multiplications can be done, but limited multiplications with high speed. Only four operations can be done in parallel, but high speed. Okay. Complex control logic in case of CPU. Then here control logic is okay, inbuilt, maybe small control logic for each row or each column or each processing element, there is a small distributed control logic. Okay. A small control logic, if you see multiple control logics are present in this yellow color blocks, small yellow color blocks. Okay. Then built for parallel operations, many parallel execution units, ALU, graphics, the best known as easy of parallelism. And here if you see large cache memory, that orange color block is the cache memory. Okay. Maybe megabytes of cache memory is going to present in this large cache memory in CPUs. But cache memory is also present in the GPU, but it is a very small limited cache memory, small cache memory. Then optimized for serial operations in ALUs, higher clock speeds, so CPUs. And here parallel shallow pipelines, CPUs, shallow pipelines, that is maybe less than 30 stages, but whereas GPU is deep pipelines, hundreds of stages. Pipelining stages are more in the case of GPUs. GPU deep pipelines, hundreds of stages, these are shallow pipelines. Then latency, low latency tolerance, the high latency tolerance here. Throughput is concerned, this GPU throughput is high. Hello? Chalo. latency tolerance, this is high latency tolerance. Newer CPUs have more parallelism, okay, and here new GPUs better flow control logic because more CPU like, this category more memory access, don't have one way pipeline, system more, okay, right, thank you. So this is the main just brief difference between CPU and GPUs, okay. What is CUDA programming? So because the software program also, it should support parallel execution, okay. The program that you are writing on CPU, the same program we cannot run directly, we cannot run on GPU as it is, okay. We have to modify the programming structure so that it can be executed parallelly on the GPU, okay. For that we are going to use the CUDA programming. The Compute Unified Device Architecture is a parallel computing platform and programming model developed by NVIDIA. It enables developers to use GPUs for general purpose processing, offering significant speed up for parallel tasks, okay. So, okay, I am not going to continue this, I will stop here only. This for just for time, okay, otherwise shall I continue? Okay, no, whatever I planned that I will continue. So morning I think we have skipped some of the slides, just I will cover just few minutes about that internal one example architecture will take, that is general. I discussed about the FPGA fabric generally. Yeah, this is one architecture. This 7 series FPGA, this is 7 series FPGA, okay. So what like Vertex 7, but it is not Vertex 7 family, 7 series FPGA, Vertex 7 is different, this is a Zinc FPGA, okay. So in this FPGA, one more fabric component I forgotten, that one more fabric component is processing core also it is present. Processing core, in addition to that whatever we have discussed in the morning, interconnect resources, okay, and interconnection what you call interconnector resources, connections, vertical horizontal tracks, lanes, as well as switch matrices, and also dedicated memory and dedicated computing blocks, DSP blocks, and plus CLBs, and plus one more is processing engines, my processor cores also present. In Vertex 4 FPGA there are 4 processing cores inside, okay. PowerPC processing core engines are present inside. PowerPC Motorola PowerPC 32-bit RISC architecture. processing cores. That means everything, the processing core, that means CPU. Okay, here CPU is present, memory is present, then computing logic, CLBs, so plus interconnecting structure, everything is present inside the FPGA fabric. Okay. So, this is Zinc FPGA, Zinc evaluation, that is the family name, that is Zinc, like a vertex, so Zinc. Okay. So, in the Zinc evaluation, if you see the processor, there is again the processor, suppose you want to interface to the FPGA, externally we have to connect the processor core. Okay. But maybe in some FPGA there is an on chip also, like a vertex core, there is a processor core, PowerPC processor core, 4 processor cores are present inside the FPGA. Similarly, in the Zinc also there is a processor core, like here ARM A9 processor, ARM processor core, dual core ARM A9 processor core is present. That blue color is the blue color one block, that is ARM processor core. That yellow color one is FPGA fabric, whatever I discussed in the morning, that is FPGA fabric total. Okay. So, this is Zinc FPGA on chip resources. So, here in the Zinc before this glue logic, BRAM, DSP is there, but then later micro blaze architecture also there, soft core, that is a soft core processor. It's accelerator 1, accelerator 2, microprocessor, soft core, soft multi-core plus accelerators, that is the next version, that is a micro blaze. The next is Zinc. Zinc is dual core A9 plus accelerators, GPP plus accelerators. Okay. Then the future Zinc may be GPP, next generation GPP and multi-core processors, that P is processing engines like a GPP structure plus accelerators, that type of applications we can implement on the future Zinc FPGAs. This is for future Zinc FPGAs. Now, currently we are using this Zinc FPGA, okay, dual core A9, dual core means 2 cores. Okay. Yeah, if you just see the evaluation, this is a programmable portfolio, Spartan 6, Spartan family, Spartan 6, Spartan 7, then RTX, then Zinc 7000. Okay. So, here Spartan 6 family we can use for image processing, safety and security, the precision control, sensor fusion, any to any connectivity. So, for all these type of applications are maybe it is suitable. So, mainly image processing applications, RTX 7 and Zinc 7000 FPGAs are more suitable. Okay. The next is safety and security features are included in Spartan 7, RTX 7, Zinc 7. Then precision control also it is present all these 3 families, and sensor fusion is present in Spartan 6 onwards, and then any to any connectivity it is there in all FPGAs. So, this Kintex are, so the RTX family or Kintex family is there in the 7 series FPGA, Zinc 7000 FPGA. This is processor centric platform, that is dual core ARM processor plus FPGA fabric is there in the Zinc SoC. SoC is system on chip. So, offers software, hardware and IO programmability in a single chip, incorporates dual core ARM Cortex A9 based processing system, that is a PS, and Xilinx programmable logic in a single device. Then built on a state of art high performance low power 28 nanometers high K metal gate processor technology is used in this 28 nanometer technology based processing engine, and it is RTX or Kintex 7 based programmable FPGA fabric, 7 series FPGA fabric, and up to see logical cells. Just now morning LUTs we have discussed, CLBs, cells, LUTs. 6.6 million logic cells are present in this, 6.6 million. Okay. Transceivers means high speed serial communication interface, high speed serial communication interface. So, that high speed serial communication interfaces are from 6.25 gigabits per second to 12.5 gigabits per second rate. Serial communications also present on this FPGA. Okay. So, complete ARM based processing system. Okay. that like ARM processor core, complete ARM processor core, how it is we are going to program that ARM processor core outside the FPGA, same similar ARM processor core as it is going to present on the chip. The application processor unit, dual ARM Cortex A9 processor, cache support, fully integrated memory controller, I/O peripherals, tightly integrated programmable logic, and flexible array of IOs, wide range of external multi-standard IOs, high performance integrated serial transceivers and A to D digital converter inputs. This is the internal architecture of that FPGA. Okay. See, this portion completely, the blue color one, that is processing system, PS. Yellow color one is programmable logic. FPGA fabric is yellow color one. So the total is one, that FPGA total zinc FPGA. So in that, if you see this green color, light green color, this is ARM dual core ARM A9 architecture, processor cores. These are the processor cores. That means why processor cores we can run. So ARM processing language, embedded systems we can implement on the FPGA. So right. So C programs we can able to write it, we can develop application code in C. That C code we can execute on these processor cores. Okay, and yellow color fabric is the FPGA fabric, programmable logic. Here by using Verilog or VHDL, so we can develop the logic and we can implement on this FPGA fabric. Okay, then this ash color or green color blocks are interfacing blocks. Interfacing blocks, like in embedded system, embedded controllers, there will be interfacing, like a serial interface. For example, here I2C interface, I2C, SPI interface, CAN interface, GPIO parallel lines, okay, SD card interface, and USB interface, DMA interface, and Ethernet interface. These are all interfaces are present. This is all type of interface. With this, you can connect those devices to this system. Through I2C, we can connect any system. Camera, suppose you want to connect, you can connect the camera to this FPGA, okay, or USB, through USB you can connect any device, USB enabled device, you can connect to this system through these interfaces. That means it is a powerful FPGA we can use for in embedded applications with a lot of external communication interfaces plus FPGA fabric and processing cores are present inside the system, this FPGA system. Okay, system on a chip. It is programmable or reconfigurable SOC. Reconfigurable means, so just now morning reconfiguration we have studied. That's why this is a reconfigurable SOC. SOC means system on a chip. System means processor is present here, because this is a processor, memory is there, memory interface is there, plus on chip cache memory is also present. We can connect external memory, DDR memory. Okay, right. So plus FPGA fabrics, all interfaces, processing system, as well as the memory is present. That's why we call it as this is SOC, system on a chip. Complete system we can implement on this FPGA. The internal the details of that block diagram. So application processor unit, memory interface, I/O peripheral interface, interconnect. That is about PS processing system. Programmable logic is PL, PS and PL. Okay, so this is internal blocks of the processor core. That ARM processor internal blocks. Two dual core ARM processors are there. No? Each internal there is a arithmetic logic unit, ARM Cortex A9 CPU. This is ARM processor core. Plus floating point unit, that is a floating point arithmetic operations also we can execute on this processor core. Then memory management unit, we can connect this processor core with external memory, DDR type of memory. Okay, DDR means 4 GB or 2 GB, 8 GB memory we can interface. Then cache memory, on chip cache memory also present here. 32 KB instruction cache and 32 KB data cache memory. Okay. So that type of processor cores dual, two are there in this, plus L2 cache memory also, 512 KB L2 cache memory, L1 cache memory and L2 cache memory, and then also on chip some memory, small memory is also present, that is a 256K SRAM memory is also present, okay, and 8 DMA channels. You studied DMA, right? So DMA channels, 8 DMA channels also present. Okay, same thing it is again, once again it is shown here. So if you see APU, each APU internally contains ARM Cortex A9 CPU, Neon unit, floating point unit, memory management unit, L1 cache. Snoop controller is a cache related. L2 cache, system level control registers, accelerator coherency port, on chip SRAM, DMA controller, general interrupt controller, timers. So the pins, dedicated pins, 54 dedicated pins, because these pins are shared between multiple functions. So but external is concerned MIO, so 54 dedicated pins are there, but these are shared across multiple functions, okay. It can be shared for DMA or USB or maybe SD card or maybe, so the different functionality is there in this, okay. These pins are shared across multiple operations, multiple functions. Input output peripherals, 2 gigabit Ethernet controllers, 2 USB controllers, 2 SPI controllers, 2 SD card controllers, 2 CAN, 2 I2C, 2 UART, 4 32-bit GPIOs, static memory interfaces, NAND and NOR SPI, quad SPI flash and trace ports. These are all features of this IO processor interfaces for the input output peripherals. Memory is concerned, DDR memory controller, quad SPI controller and static memory controller. These 3 memory controllers are going to present inside the FPGA fabric. This is the DDR memory controller block diagram internally, external DDR memory interfacing. Interconnects are actually internal FPGA fabric to CPU processor core, the interconnections also there. FPGA fabric to the processor core interconnect. That interconnect is primarily mechanism for data communication. Interconnect located within the PS comprises of multiple switches to connect system resources using AXI. AXI point-to-point channels for communicating address, data and response transaction between master and slave clients. So what is AXI? AXI is a part of ARM AMBA 3.0 interconnect, okay. So if you see interconnect features are, the interconnect is based on AXI high performance data path switches, Snoop control unit, L2 cache controller, and interconnect switches based on ARM NIC 301. So central interconnect, master interconnect for slave peripherals, slave interconnect for master peripherals, memory interconnect, OCM on chip memory interconnect, AHB and APB bridges. So this is your AXI interconnect. So this is the AMBA interface, that AMBA is advanced microcontroller bus architecture, okay. This is for interconnecting a FPGA fabric with processor core. So in this APB, AHB, AXI, so this is sub interfaces, or maybe these are actually AMBA 3.0, this is in standard 3.0. So in that these are the bus interfaces basically from AMBA bus architecture. AMBA bus architecture internal sub interfaces, okay. So peripheral bus, high performance bus and AXI bus. AXI is here advanced extensible interface. This is a Xilinx FPGA, mainly for Xilinx logic interconnection purpose this AXI used. Xilinx FPGA fabric interconnection purpose only this AXI is developed. But this is developed by ARM organization only, AXI, AMBA bus. But HB, APB, these are all part of the AMBA only. Yeah, just see this and quickly I close this. AX interconnects AMBA, if you see APB, AHB, AXI, ATB. So, in this AXI again 3 categories. AXI is, what is AXI? AXI is, I told you know, this is advanced extensible interface. Advanced, this APB is advanced peripheral bus or AMBA advanced peripheral bus. What is APB? Peripheral bus only. A for advanced we can use or AMBA we can use. A is AMBA actually. This AMBA, from the AMBA only this has derived, these 3 bus interfaces. Peripheral bus, AMBA, peripheral bus, AMBA, high performance bus. So, but here advanced extensible interface, that means you can also use A, advanced peripheral bus, advanced high performance bus, advanced extensible interface. Extensible. This advanced extensible interface AXI bus, this bus is mainly for interfacing FPGA fabric with the processor code. So, this AXI again divided into subcategories. AXI 4 memory map, AXI 4 stream, AXI 4 light. These are the 3 subcategories of AXI. That is AMBA 4.0. This is AMBA 3.0 is these categories APB, AHB, AXI. Okay. So, if you see the difference, AXI 4 memory map full, traditional address data burst, single address multiple data. Burst transfer operations, if you want burst transfer, then you have to use AXI 4 memory map interface. This is a traditional address data burst only. The light transfers are AXI light, one more is there, AXI 4 light. This is a traditional address data, no burst transfer is allowed here. It is only single address, single data only we are going to transfer in AXI 4 light. Okay, you can use AXI 4 light or AXI 4 full or streaming. Any one of these 3 interfaces you can use to communicate with the processor core inside the FPGA with FPGA fabric. Okay. So, each Zinc 7000 device contains same PS with PL and IO resources vary between the devices. There are different types of 7000 series devices, Zinc devices. So, 7010, 7015, 7020, they are dual core, whereas 7007, 7012, 7014, those are one single core only. The PL based is the PL based RTX 7 series FPGA logic. PL is RTX 7 only, all FPGAs RTX FPGA fabric. Then coming to 7030, 7035, 7045, 7100, but here only PL is varied. PL is Kintex based. PL is Kintex based FPGA fabric remaining. So, but the device side, processor side remains same. So, PS and PL can tightly or loosely coupled using multiple interfaces and other signals that have combined a total of 3000 connections. PL can be a separate power domain from the PS, saves power. So, different power up operations also possible, different power modes. Yeah. So, configurable logical block, the PL side, 6 input lookup table, that is why morning we have discussed lookup table size. So, all these FPGAs 6 input LUT, memory capability within the LUT. Okay, each LUT if you want to convert into memory, it is possible, memory capability. Then register and shift register functionality, that means each LUT we can also convert into a shift register. If you want to, you can use as a shift register also, that possibility is also there. You can convert that LUT into a shift register. And cascadable adders. So, for example, ripple carry adder type of adder, suppose if you want to implement 32-bit adder, 64-bit adder. So, that cascading type logic is automation, automatically it will be cascaded. Okay. Cascadable adders also we can create with the help of the LUTs. But memory is concerned 32 KB block RAM, 32 KB, KB is kilobytes here, 32 KB kilobytes of block RAMs. How many are there? We don't know. How many are there in this? Not given. Dual port, okay, and up to 72-bit wide. That means we can increase the width also, memory block. Memory width also we can increase. Width is, memory width 8-bit. If we connect in parallel, we can increase the width. If you connect in serial, increase the size. Configurable as a dual 18 KB. So this is 32 KB, no? So configurable as a dual 18 KB. We can configure that into 18 KB, dual 18 KB also. We can convert that into two 18 KBs. Or you can increase the 36 to 72 KB like that, we can also increase. Programmable FIFO logic, we can also convert into FIFO. We can use as a FIFO. Built-in error correction and circuitry, that is memory error correction circuitry also built in this. DSP slice. DSP slice, we have seen DSP slice morning. So here 25 by 18 2's complement multiplier accumulator, high resolution, 48-bit multiplier accumulator. 25 by 8 2's complement multiplier and accumulator, high resolution, 48-bit by 48-bit multiplier and accumulator also possible. 25 by 18 2's complement multiplier accumulator or 48-bit multiplier and accumulator. We can configure that DSP. Power saving 25-bit pre-added to optimize symmetrical filter applications. 25-bit pre-adder. Then advanced features like optional pipelining, optional ALU and dedicated buses for cascading. These are some of the features of the DSP. Clock management, high speed buffers, routing of low skew clock distribution. Clock will be actually not, clock is actually clock managing circuit is going to present. That will distribute the clock across all CLBs in a tree fashion. So equal length will be maintained. The clock skew will be eliminated. So low jitter clock generation, jitter filtering, that clock management will take care of this. Frequency synthesis and phase shifting, configurable IOs, input output pins, blocks, high performance select IO technology, high performance decoupling capacitors within the package for enhanced signal integrity. So this is IOs, about input output pins, and a digitally controlled impedance that can be three stated for lowest power or high speed IO operation. High range IO supporting 1.2 volts to 3.3 volts, high performance IO support 1.2 volts to 1.8 volts. That is the IO technology we can use for higher range or high performance. Low power serial transceivers, high performance transceivers, low power transceivers are in these devices, low power serial transceivers. High power transceivers are capable up to 12.5 gigabits per second GTX in these devices 303545, but ours is 7020, it is not comes under this category. Okay. High performance transceiver capable up to 6.25 in 7012, 7015. Low power mode optimized for chip to chip interfaces. Okay, 7020, I think serial interface is not there. PCI Express, integrated interface block for PCI Express designs. PCI Express is serial PCI interface. PCI is a parallel interface, PCI bus, but PCI Express is a serial PCI interface logic. Latest laptops all will contain only PCI Express interface only. But compatible with PCI Express base specifications and supports generation to 5 gigabits per second. advanced configuration options, advanced error reporting, and end-to-end CRC, advanced error reporting and ECRC features. These are important features for the this FPGA fabric, the Zinc 7000 FPGA. Okay. Processor design చెప్పాలా లేకుంటే processor design అంటే it will take almost ఒక 1 hour 1.5 hour ఇదే అవుతుంది. about test bench. Then this is for monitoring display, for example, time. So okay, it will be display what is the A value, B value and product value. It will be displayed like a printf type. Okay, then the next step is you have to run simulation. Okay, so test simulation, test bench, you have to select and run behavioral simulation. So here simulation and synthesis design. No? So here this side you have to select the simulation operation layer, that you have to click, that it will run the behavioral simulation. So then you are going to get waveforms like this. Okay, this is only one case as shown, last case 255 by 255 multiplication, this is the result. This is only up to this one is simulation, source creation and simulation, test bench creation. First is project creation, the next is source file creation and test bench side creation, test bench, and testing of that source file to simulation waveforms. So once you satisfy, once you get correct output, the next step is we can create a block design. We can implement this on the board also. Okay. So for that block design, we can go for block design. Block design, where you have to do the block design. Okay, you can select the block design here. So in the block design, this symbol, add the module to the block design, the sources panel. Locate your custom module under the design sources and right click on the module name and select add module to block design. So here the block design, already whatever you have created symbol, source file, that symbol is going to be created already in the sources panel. No, in the design sources. So that we have to add to this block design. The symbol is going to be created, that we can add to the block design. Schematic symbol is going to be created for the multiplier source program. Okay, this is the symbol. Okay, that symbol we have to add in the block design. Block design is a schematic type of design, logical design. Okay, and here click on icon press add VIO. Double click on VIO, assign probe counts. Input is 1, output is 2. Input probe 1 and output probe 2. This is VIO. VIO. Okay, because here two inputs are there, one output is there. So we have to generate two inputs to this. Two input ports are required, and this output we have to take. So VIO is virtual input output IP. So by using that, we can generate test inputs to this. Test inputs we can give to this VIO. So that's why, so two input ports, we are generating a two input port and two output ports, because two output ports are, you see, this is your multiplier. The multiplier, 8-bit multiplier. So two inputs are there here. This is 8 bits each. This is A and B. This is the product. This is the simple we have created. Product is, you will see here, what is the product? Result. This is the multiplier symbol here created. To test this, after implementing, you have to test this. So when we are using one IP called VIO. This is VIO IP. Virtual input output IP. Okay. This, by using this IP, we can generate the test inputs. So what are the test inputs? Two inputs are required. So that means here, this output is connected as a input to this VIO. Output. That means output also you can monitor. Output we have to check. This is virtual input output testing of it. So that means the output we can monitor that. That's why this output of this you have to connect as input to this. And here it has to generate two outputs. That is A and B outputs. So these two outputs are will be connected to here. here this will be connected. Outputs it is generating two outputs. Those two outputs will be connected. So that means this VIO should generate two output ports. These are the two output ports and one input. Okay. So that's why here VIO count. Yeah, this is port counts 1 and 2. This is input and this is output. 2 input. 1 input and 2 outputs. That IP, then that we have to select here. Okay, after selecting this, then next is then the size of the port, each port size. That we have selected ports. These are the ports. What is the size of the port? Size of the port also you have to select. Because here output is how many bits you are going to get? 16 bits. The port bit, that is the output is multiplied source code output is 16 bit. But VIO it is input. So that means input port bit should be 16 bits. Similarly, output, the VIO output, two outputs are there from the VIO. Those are connecting to input of the source. What are the sizes of the outputs? VIO 8 bits each. So here 8 bits from output 0 to 8 bits. Okay. So this is the circuit equation, that is the connection what we have drawn. This is a similar connection is going to be you have to make in the block design. So simply we can draw that. Okay. So just take that VIO symbol from the IP. The design source is there. This VIO IP is there. That you just select and paste. And this also you can select and paste in the design menu. Then interconnect these two. Simply interconnecting this, you can get like this. One is VIO, one is multiplier. Okay, that one is multiplier, this is VIO. Okay, the next is up to this is sufficient, okay, for testing of the multiplier. You can do, because that VIO is used to generate the inputs. That about how it is going to generate, the generating inputs is through keypad only. The keypad you can enter the inputs. So 8-bit inputs were selected, right? So that if you just type this, automatically it will go to that VIO input that will be fed as inputs. Okay? So here, these inputs, VIO will be, so because here VIO, if we interacted, we can interact. These VIO inputs we can set through keyboard. Generating this, we are not writing any logic here. There is no logic in this. Simply the inputs, whatever outputs it is generating here, that is through keypad only. So your keyboard, you can type the numbers here. What are the numbers you want? That numbers will go as input to this. Okay? Then output, 16-bit, that output will be displayed on the screen. So through keypad interactions, this is actually the keypad. Virtual input output, that is, this is keyboard and the display. Keyboard and display. Keyboard and display interface only. So through keyboard we can enter input and output of this product we can display on the screen. But both will be displayed. Whatever you are typing, the keyboard also will be displayed. Okay? So for testing of this logic, this VIO IP is sufficient, simple. This is for not for simulation. Simulation we have already done through test bench. This is for after implementing on the board. Okay? This logic implementing on the board, we can test the logic by using this VIO. You can give the input and you can see the output. Okay? Simulation is simple. This is not required simulation. Simulation of this is not required. For simulation of this, what we read test bench here, right? Simple. This is multiplier. So only the test bench, from the test bench, this is test bench. Test bench is giving input, multiplier, and the output we are going to see on the screen. This is the output, 16-bit output. So it is the waveforms, it's going to generate waveforms. Simulation waveforms, we can see the output. Okay, different waveforms based on the test cases. This is for simulation. This is for implementation. Implementing on the board. And but this one is through, we can enter the values only, 8-bit values, 16-bit values, 30-bit, whatever the size, board size, accordingly you can enter the values, numbers, integer number or floating point real numbers are can enter. Okay, but this is an integer, 8-bit number. Or if you want waveforms also, if you want to see, like our simulation, here we have 4 different test cases, waveforms we are seeing. Sequential logic, this is a combination logic. What is the sequential logic? That is the waveforms. Okay, so once you see the waveforms, then one more IP you have to use. That IP is IAV. That IAV is integrated logic analyzer. One more IP. So by using that IP, we can plot the waveforms also. Okay, so you see now. So ILA is a logic analyzer, you know, logic analyzer. Logic analyzer output waveforms like a CRO type. Logic analyzer is like a CRO, channels will be there. So using channels we can see the waveforms. CRO, 2 channels are there, 2 waveforms you can see. 3 channels, 3 waveforms. Okay. Similarly here, we have to see how many ports you have to observe. 2 inputs and 1 output. So that means 3 channels, 3 probes. 3 probes are required. So that ALA we can select 3 probes here. So selecting 3 probes. 3 channels, 2 input channels, 1 output channel. Okay, and same number of comparator ports. Then that's all. Okay, that just we select. So probes here, number of probes. Then number of bits assigned in ILA. Number of bits also same number, 8 bits. 8 bits inputs and 16-bit output. And number of comparators 1. So this is the final connection diagram. It's not properly visible here. The connection diagram is not properly visible. Light will delete. Okay, this is a multiplier. This one is multiplier, and this one is VIO, and this one is logic analyzer. Okay, multiplier, virtual input output, and logic analyzer. Logic analyzer, how it is connected? See the multiplier inputs, same inputs are connected as 1 probe. 2 inputs are there. 2 inputs are just connected, and output also connected. Okay, this out the multiplier. 2 inputs and 1 output is there. Those 3 just connect to logic analyzer, that's all. Okay? So 2 inputs, this input is connected to logic analyzer. See, only logic analyzer can be used for testing without having a VIO. Can we use VIO or can we use only logic analyzer for testing the circuit? Logic analyzer is for only just for seeing the waveforms, that's all. Okay, input output waveforms. So only logic analyzer is not sufficient. Logic analyzer is just only output monitoring, like a CRO type. It is not generating test input. Test inputs are generated through VIO only. Right? Only logic analyzer not sufficient. Without logic analyzer also we can test by using VIO. Okay? So the next step is we have to assign pins. We have to assign the pins because this is FPGA core planning. Okay, in the core planning, the pins will be there. This FPGA internally contains some, how many pins? 400 pins or 300 pins? Okay, so some around some 200 pins are there for this FPGA. We require how many pins? 8 in 8-bit inputs, 2 inputs are there. Okay. Then 16-bit output. Okay, 16-bit output to 8-bit input ports. So that means 32 pins. 32 pins plus 1 clock pin. So 33 pins we have to assign. Pins of the FPGA you have to assign. Okay. The pins of the FPGA can be selected package pins. So one is clock we are selecting here. Just clock. Clock is enough. Not required. Okay. This is internal operation. So if it is external connection to LEDs or switches, you have to assign the pins. This is inside the FPGA. You need not assign any pins here because internally the ILA IP is generating. The VIO is generating input. Okay, the output is again. So we can display through VIO or ILA. That's all. No pins connection is not required. It is internal logic IP testing. Right? If you want to connect externally, if you give inputs. So for example, after programming the FPGA, this is FPGA, you program this multiplier. Okay, this is multiplier logic implemented on the FPGA. And the pins will be there, all the pins. There are so many pins will be there here. Okay, so for these pins, if you want to test it, so you have to assign this multiplier is 8 bit. This inputs are 8 bits. Product is 16 bits. Okay, if you want to test these inputs, you have to feed through some external input. The switches are any test generator logic. So this is the external input suppose you connect. Then all these 8 pins you have to connect to these FPGA port pins. Again these 8 pins will be connected to 8 FPGA port pins. The 16 pins also you have to connect to 16 pins of the FPGA port pins. 32 pins are required. So here 8 plus 8, 16. Here 16, 32 pins. 32 pins we have to use. But without using this external connection, what we are doing is, so we are actually using one IP, one IP. This IP itself it is feeding to this simply inputs internally. This is internal to the FPGA, inside the FPGA. Output also same. Okay. So right. This by one IP is there inside the FPGA. And that VIO IP is generating test inputs to this. So you not feed external inputs, external output will not come. The pins connection is not required. Okay. So only one this IP clock connection only had to be one clock pin, external clock pin, because external clock source is there. This is the clock signal is going. Clock signal is there from one pin. Right? That clock only we have to connect to this. That's all. Nothing else. Only one pin assignment is required. Okay, understood this? So that clock pin is a default only, one pin number, it is a fixed pin only always. So that is Y9 pin, one pin is assigned to clock. Clock is connected on the board to on particular fixed pin only. That pin only at select clock pin. Okay. Then next is you have to create one constraint file. Constraint file is pins assignment file only. That is XDC file. That file is a constraint file that will contain only these pins assignment. So right, save the constraint file with the name. So some name you have to give constraint file name. So demo is written here, demo. Then press OK. Then it will generate the bit stream. The next is you have to generate a bit stream. After doing this, next we have to generate a bit stream. Morning you have to generate a bit stream. That bit stream will be generated here. Okay. So after bit stream, then we can also see the reports also. So all these reports also, synthesis, after synthesis only it will become modules. So these reports are indicating that this logic block, how much power it is consuming, total power of 0.0185 constant power. Okay. Then temperature, thermal margin. Then here this is the constant power distribution. Dynamic power, static power, 98% of static power only it is consuming only. So 2% only dynamic power, 0.002 watts. Then again with dynamic power, the distribution, power distribution, FPGA board. The Gian Z board is a Z board, 7020 Gian FPGA board. Okay. So the next is validation. After creating the validation on the block diagram, then create a wrapper file, create SQL wrapper file. After creating wrapper file, So then what you are doing here, you are assigning wrapper failure, assigning radix values to VI board. So here we are assigning input outputs, right? Input outputs it will display like this. So you just type the input outputs here, then you will get the output. VIO input outputs. Okay? So one input per VIO. Input is, what is the input per VIO? VIO input is output of the multiplier. VIO output is input to the multiplier. Okay? See, this is the waveform. This waveform is from ILA. ILA, because we are using ILA will give the output waveform. Okay? So, but this is implementation, after implementation on the board. Okay? What you do is now, so the Gopalakrishna is our research scholar, is doing his PhD here. Okay? So he is going to help you to do, you can do this multiplier logic on your own. Okay? Maybe you can also test on the FPGA board also. Then to complete that testing, then you can hands-on system. Okay? You can virtually you can implement and test it. Okay? So we'll help you. Then he will demonstrate you. He will demonstrate step by step. You can follow that steps. So you just follow, you just power on all the systems. Power on so you will instruct, okay, click on this, you have to do that. Okay?
Like this.
Yes, this change. Nice. Actually, systems on. Okay. So this window is there everywhere?
So click on Viva 2018.3. Click on this icon.
Nice.
So click on Viva 2018.3. Click on it.
Yes.
Okay, go to the file. So create project.
You cannot only install.
So as the desktop you have icon, Viva 2018.3. Go to the file. All of you go to the file. Not you okay?
Everyone.
Go to the file. Select the project. Click on new project. Click on it. Okay. So this window is open. Create new Viva project. So click on next. RTL project. Select the RTL project. Select the RTL project, click on next. Now in this one, go to the boards, you show a jet board, Gian evaluation and development kit. So select that one. Click on next. Go to the boards, select the jet board, click on next. Okay, done. Have you done? So this is a project summary. So this is the device part number XC70020 CLG484. This is the Gian family. Okay. So this is our device part number. So this is the Gian 7000 product. So click on finish. Okay. Next up. Go to the sources, design sources. Okay. This one, click on plus icon. Go to the sources. This one, plus icon. Add sources. So click on that plus icon. Go to the sources. So click on plus icon. Here. This one, this is the plus icon. Go to the sources. Click here. Plus icon. So you will be open this window. So in this window, you will be select the middle one. Add and create design sources. Now create the source file. So add and create design source. So click on next. Select the middle one. Add and create design sources. Click next. Okay. Here click on create a file. Here give your name. So now we are designing multiplier. So give it multiplier. Underscore 8-bit. Any name. So file name you can assign any file name. So multiplier underscore 8-bit. Click on OK. Okay. Next finish. Click on finish. So now it is asking module name. It is not required. Click on OK. So click on OK. So the module definition has not been changed. Or you should want to change use this value. So click on S. Click on S. So it is updated. So after that our module is created. This is our module. Mal underscore 8-bit. Okay, done. Double click on this module. So what happens for 8 bit? You should double click on it. It is open this window. This is our code right here. Okay. Write down that code. Time scale already there. Time scale 1 nanosecond by only just you can write here from here to here will be random code. These are not required, these are the comments. These are not required. Just module multiplier input A, input B, output, close bracket, and assign result A to B and module. That only. Total 5 lines. Completed After that, you can save it. Save the file. Here, this is the icon. Save the file or Control S. Click on save the file. Again, click on plus icon. Again, click on plus icon. Go to the sources. Just click on plus icon. And the radar create the simulation sources for test bench. For test bench, select the radar create simulation sources. After saving the file, go to the sources. Click on plus icon and select the radar create simulation sources. So click on next. Click on next. Again create a file. Here write the name, file name, test bench. Okay, test bench. Click on OK. Go to the sources. Go to the sources. Select, click on plus icon. Okay. So select the radar create simulation sources. After that, click on OK. So click on next. It will open this window. Create source file. Just give the file name. Any file name. Okay. So click on OK. So next, click on finish. Just click on finish. It is not just click on OK. It is asking yes. Same, how to create the source file, same like test bench also. So click on plus icon, select the create the simulation sources and create a file, save it. Click on S. So next that will be created here. See, this is the simulation sources. Expand here. This is the test bench or test bench. So what I created file, that is our test bench here. Expand the simulation results. So our test bench will be shown. Double click on that. Double click on that. Middle one for source file, last one for simulation. Okay, so here write the test bench code. I have to write down the test bench code.
already existing was.
Completed. Just assign some values, new values. Just sequence. Initial again A value and B value. Copy first one copy type right, this one A equals to C equals to this one copy and paste here, just change the values. okay, you can do later otherwise. Just copy the code. Go down. Now. Copy paste only one by one. Sequence is enough. Let us sequence, same sequence you can copy. This sequence you can take, type, same sequence you can copy multiple times. Just to change the values, A and B values you can change it. Last one it will be write this one, monitor the result. Take photos, and later you can do it. Okay. So now see, same code, after completing it, copy the code, you can save it. Okay. So next one it will be go to the simulation. This one simulation. Go to the simulation. Run. Click on run simulation. Click on run simulation. Just note down the steps. Simulation is not. Okay. So click on run simulation. Run behavior simulation. Click on that. Okay, all of you done? So go to the simulation. So run simulation. Click on run simulation. Run behavioral simulation. Okay, completed. So now it is open one window, untitled window. So click on that. After completing the simulation, it will be open one window, untitled window. Click on that, like the simulation results will be displayed here. Okay. Now right click on this one. Right click on value, right click on this one. Go to the radix. Unsigned decimal. Select the unsigned decimal. Right click on this one. See, right click on this one. Okay, go to the radix. Select the unsigned decimal. This 255 value. Same like second one also. Right click on the radix. Select unsigned decimal. The third one also. So 255 into 255. So you multiply, that is the result. 65,025. Okay. Have you done? After that, click on run. So right side, left side, now create block design, IP indicator. So create block design, click on it. So it is asking name, any name is given here. Design one or any one. So multiplier, or design name is multiplier, click on OK. Okay, so now go to the sources. So right click on multiplier. to the create block design. Create block design. Right click on the module. Right click on the module here. Module to the block design. Add module to the block design. Now click on plus icon. Click on plus icon. Here go to the block design. Click on the plus icon. Type VIO. Type VIO. Virtual input and output. Okay. Click on it. It is added. This is our VIO. Now just create block design. Click on block design. Okay, right click on this module. Right click on this module. So module water grade. Right click on that. Select this one. Add module to the block design. So after that, click on plus icon. Click on plus icon. Type VIO. Type VIO. Click on plus icon. Type VIO. So virtual input output. Okay, click on it. So it will be created one VIO. So double click on that. So double click on that. Here. So how many input probes are required? Only one input probe. So the module output is input of VIO. So that's why one input probe is enough and output ports are two required. So one input port, two output ports. And next one, the probe input ports. Go to the here probe width. So what is the probe width? The input is how much? 16. Input is 16. Next the probe outputs. Go to the port output ports. So probe outputs is 8 and 8. Input A is 8, B is 8. Click on OK. Okay, click on OK. So now it is showing. So this is 7:0, 7:0. This is inputs. This is the output. One output, two inputs. These two inputs are connected to the two inputs of module. The output of VIO is connected to the input of module. And the VIO input is connected to the output of the module. Just drag it. Double click on VIO. So now probe count. Input probe count is 1. Output probe count is 2. The VIO output is input of module. Module means or module is RTL. Multiplier underscore 0 is the module name. So now the probe width, the input probe width is 16 bit. The result is 16 bit. Next the output ports is 8 bit and 8 bit. Just click on OK. So now this will be modified. The probe output is 16. 0 colon 15 is 16 bit. This is 7 colon 0 is 8 bit and 8 bit. So just these two are connected to these two. This one is connected to this one. The VIO input is connected to the output of RTL. VIO output is connected to the input of RTL. Okay. Next click on plus icon. Again click on plus icon. Type ILA. Integrated logic analyzer. Click on plus icon. Type ILA. Integrated logic analyzer. Okay. Click on that. So ILA is created. So double click on that. So double click on that. now select the NAT2. This option not AXL. AXL interconnect is we are not using. So NAT2. So just connect the NAT2 option. Select the NAT2 option. And the number of probes, how many probes are required to input on output? Total 3 are required. So just type the 3. Select the NAT2 option. And the number of probes, 3 probes are required. Just type the 3. Okay. After that, probe width. Select this option, probe force. So in this probe force, the first one is 8, second one also 8, third one is 16. 8, 8, 16. Click on OK. Okay, click on OK. Now the 7:0, 7:0, these are the input of RTR. Just connect the input of RTR. Okay. Next, the last one, 16. The probe is output of RTR. Just connect to the output of RTR. This is the block design. Next, the clocks are there, 2 clocks. The VIO clock and the IMA clock. These 2 clocks will interconnect. The first one clock will be select and right click on it. One clock select and right click on it. And make external. This option, make external. Select the make external, click on it. Make external, click on it. So the external clock is created. So now this clock is connected to this clock. Okay. So now you can refresh it. This is the refresh. Refresh it. Automatically it is refreshed. So next one, validation. Our design is correct or not. You can check it. So this is the validation. Validate design. This option. So click on that. So validate design. So validation successful. There is no errors or critical warnings in this design. What we done? This is the validation option. Just click on it. Okay. After validation completed, go to the sources. Go to the sources. Here sources is there. Here. So go to the sources. Right click on the design. Our design. What are the design? Right click on that. Create HDL wrapper. Create HDL wrapper. Go to the design, right click on that, create HDL wrapper. So click on that, it is asking auto update. So select the auto update, second option, that recorder manager wrapper and auto update. So click on OK. So our design will be modified. Previously it is design _1, now design _1 wrapper. So it is updating. So wrapper is created. Okay. So now after that, go to the open elaborated design. Go to the open elaborated design. Click on it. The left side is there open RTL analysis. Please go to the RTL analysis, open elaborated design. So click on that. after that, see, expand clock here. So just if you click on that, this is expand the clock and expand the scalar codes. So now clock underscore 0. So now only this thing you can select. So now here just click on that. This what are the pins available in Jetboard? All pins will be showing. So just type Y9. So Y9. So it is showing. Just select that one. And this is the default LV CMOS. The CMOS voltage you can select LV CMOS 33. This option you can select LV CMOS 33. Click on pure. So select this one. So only expand the clock. In the clock scalar codes is there. Expand again that one. It is showing clock underscore 0. This clock underscore 0 package pin you can select and say like IO standard LV CMOS 33. Okay, after that you can save Control S. After that you can save Control S. So it is asking constraint file. So constraint file name. After select the pins, just Control S, save. It is asking name, constraint file name, assign any name. RTL analysis open alphabet design.
Side. Confirm. Okay. शक्यता नहीं
Okay, program device. Here program device. Open one target. After that program device. We need two files. One is bit file. What are created bit file. This is design one wrapper bit file and design one wrapper and there. So just click on program. So now that is one is hardware ILA and hardware EAOs. Two files are created. This is EOS and this is ILA. Go to the EOS. Okay. Click on plus icon. Click on plus icon. This three ports. These three probes. Select these three probes and click on OK. Okay. So now this will be changing. So radix. Go to the radix. Unsigned decimal. This also radix unsigned decimal. All you can mark it and it will be these are the inputs, right? This is 7:0 and 7:0. These are the two inputs. This is the output. So now the input values you can assign. So 255. 255. So click on OK. Okay. Now go to the ILA. So now the value will be 65,045. Okay. Now go to the ILA. The results, simulation results. Just you can run it. The result will be showing. So FF. Here also radix unsigned decimal. Here also radix unsigned decimal. Here also radix unsigned decimal. So now this is 255 and the declared value 65,025. So if you any values you can modify here only. The EOS you can modify it here. 10, 1, 5, 50. So 10 into 5, 50. The same value will be 50 here. Just run it. So 10, 5.
Ranji last.
Sai. Anish closer. Some closer. Anish. Some closer.
5 minutes foundation.
2 minutes foundation.
Okay, right. Like this, you can implement any circuit on the board with the help of ILA and BIO IPs. Okay, so just now we have just verified a multiplier logic circuit suite implemented on the board and tested with the help of DIO and IAGA. So DIO is directly can do the inputs to the keyboard and result will be displayed on the screen. IAGA will show the waveforms. Okay. So, so we'll close this session today and we'll meet again tomorrow morning at 10